July 1961. Vol. 10, No. 7. Open Shop Programming Speeds Research and Production. Ching Automa. The Trouble It. The CC. Compilers. TV. Underscore. I. 2. TQ the engineer. Who needs the magic of Mercury? AE. Ken. DO. If you're stymied by switching problems in data processing, automatic control or high speed keying, then consider the unusual attributes of AE Series V51 Mercury Wetted Contact Relay. This fleet switcher can be driven at speeds up to 100 operations per second, completely free from contact bounce. It requires no maintenance within its life of over a billion transfers. The contacts can switch dry circuits or handle loads up to 250 volt-amperes. Operate and release time is approximately 3 milliseconds. Contact and armature assemblies of the V51 are hermetically sealed in a glass capsule with a high-pressure hydrogen atmosphere. Mercury wetting continuously renews the contacts, eliminates wear, erosion, welding, and sticking. Operating sensitivity is 250 milliwatts, minimum. AE engineers will be glad to aid in applying the V51 to your designs. Ask for circular 1988 covering full specs on the V51. Right. The Director, Control Equipment Sales, Automatic Electric, North Lake, Illinois. Automatio Electrio. Subsidiary of Olm for JL Telephone and Electronics. Computers and Automation for July, 1961. Ali. Con. L11 Clin. Regu. \n in. Park. NY. 1, Pa. Del, / Imp IE. Renan. New. Inari. Tis OLL. Either. Se Re. Ting. Ush. York. York. DAP. Wine. And. Perry. Phase. Chem. Lab. Core. GER. SIG. Ignal. Dotville. SYS. Work. Inna. Unti. Own. Are the. L1ized. Tex. Tex. Anna. Stan. VIS. Stan. 8/ Toga. S. / Ages. Lter. 3/ 9/ LRY. 1/ 1961. You can spread a computer all over the map. Now, company-wide data processing integrated into one efficient SysNL. A Philco 2000 electronic data PROC. SEing system at headquarters is tied through a Philco data link system, using Philco microwave or leased lines, to remote Philco input-output systems. Data from remote stations as well as local computer inputs are coordinated and pre-processed by a Philco 2400 data handling system to produce new heights of computer efficiency. For more complete information write PHILCD PINWJ lore T/ZE2//oralt, LICR registered. Philco data link system. Characteristics. Inputs, any combination of Data link and local inputs. Checking, matrix parity on each. Variable length message. Transmission direct between. Core storage memories. Stored program correction. Of transmission error. Direct conversion between any two devices and code formats. Data rates, up to 1 million bits per second. Philco Corporation Government and Industrial Group Computer Division, 3900 Welsh Road, Willow Grove, PA. Computers. Adult automation. Computers and data processors, and their construction. Applications, and implications, including automation. Volume 10. Number 7. July, 1961. Established. September 1951. Edmund C. Berkeley Editor. Neil D. MacDonald Assistant Editor. Moses M. Berlin Assistant Editor. Patrick J. McGovern, Assistant Editor. Barry F. Shepard Assistant Editor. Contributing Editors. Andrew D. Booth. Ned Chapin. John W. Carr, 3. Alston S. Householder. Advisory Committee. Morton M. Estrahan. Howard T. Engstrom. George E. Forsyth. Richard W. Hamming. Alston S. Householder. Herbert F. Mitchell, Jr. SLA and Service Director. Edmund C. Berkeley. 815 Washington Street. Newtonville 60, Mass. Decatur 25453. Advertising Representatives. Los Angeles 5/Ventworth F. Green. 439 So. Western Ave. Dunkirk 7 to 813 5. San Francisco 5. 605 Market Street. A.S. Babcock. Yukon 2 to 3954. Elsewhere Edmund C. Berkeley. 815 Washington Street Decatur 2 to 5453. Newtonville 60, Mass. News of computers and data processors. Across the editor's desk. Inserted between pages 16 and 17. Front cover. M. Mori for a Pneumatic Digital Computer 1, 6. Articles. Open Shop Programming at Rocketdyne Speeds Re. Search and Production, D.J. Brahamate. Automated Teaching, E. F. Cooley. 10. The Trouble with Commercial Compilers, John H. Hughes. 13. The Coming Technological Society, Dr. Simon Ramo. 15. Readers and Editors Forum. Computers in Nuclear Engineering, Dr. Jan Paul. 6. Computers and Armaments, Carl H. Groom and the Editor. 6. Restless Giant, Walter Brandenburg. 22. Calendar of Coming Events. 22. Reference Information. Who's Who in the Computer Field, Supplement. 24. Books and Other Publications, Moses M. Berlin. 28. New Patents, Raymond R. Skolnick. 29. Index of Notices. Advertising Index. Computer Directory and Buyer's Guide. Frequency of Computers and Automation. Glossary of Terms. Manuscripts. Reference and Survey Information. Who's Who Entry Form. See May. See May. See April. See February. See May. 30. Page 24. Page 12. Page 28. Page 12. Page 24. 9. Underscore 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 dash equals C equals O underscore M underscore P underscore U dot TERS and Automation is published monthly at 8:15 Washington Street. Newtonville YL3 Erkley Enterprises, Inc. Fintia Inu SA-. 4. Subscription rates, United States, $15 for 1 year, $29 for 2 years, in. Cludding the June directory issue, Canada, add 50 C a year for postage, foreign, add $1 a year for postage. Address all editorial and subscription mail to Berkeley Enterprises, Inc., 815 Washington Street, Newtonville 60, Mass. Entered as second-class matter at the post office at Boston, Mass. Postmaster, please send all forms 3579 to Berkeley Enterprises Incorporated, 815 Washington. St., Newtonville 60, Mass. Copyright, 1961, by Berkeley Enterprises Incorporated. Change of address, if your address changes, please send us both your new address and your old address, as it appears on the magazine address imprint, and allow 3 weeks for the change to be made. Computers Lind Automation for July, 1961. N. R.A. Ford. Corp. Th. APA. N.A. Offic. Ent. Kate. Number 1. Inven. Ansen. Comr. Ton 2. Each. J. 2,969,5. N. N. And. 2,969,5. To. MK. Needy. 2,969/ N. A. Chin. 2,969. Turb. Ural. Car. 2,969. And. Cali. CIT. Shiv. Tal. 2,970. /S. AI. 2,970. Ma. / Regi. 2,970. N. / Ori. 2,970. PAR. N. 4. 2,970. T01. We. BM. 2,970. N. Rho. GRA. Terry. 2,970. Pet. N. Key. N. .970J. Ma. Pa. AC. 2,970. N. GE. CA. Log. COL\1. Review. NS in. The. ES of. Value. IAG. Into. Lip ear. In. Mtekl. 1. ULA. Inc. YI. Back. Odak. Rural. Yulal. Is a. Entire. Rarn. Mong. Sub. Lpud. Truck. Stern. Ian. 60. The. V Hill. New. 6 pp. Athe. Is R. As a. Liver. S in. D in. Lysix. Attical. Ding. Ons. Jatotic. Idesty. Uds. In. And. The. PROC. Nina. Reov. Prob. And. MI. Sand. Inc. YI. Cope. Leary. mner, e, in, lud, and, iable, ential, orn, new, shins, tibers, lbout, ironby, ls of, ida, loga, essel, rildex. 1961. Johnson/S. World's largest manufacturer of wax polishes. Asterisk 304 data processing system. Has proved to be a highly profitable investment. -5. C. Johnson & Son Incorporated, Racine, Wisconsin. The National 304 enables us to know today where we are today. For example, we can now bill customers on the same day items are shipped from warehouses anywhere in the United States. This has enabled us to pick up working cap ITAL equivalent to 3 days sales, an important saving. We can now take action today on inventory requirements based on last night's actual inventory and unfilled orders position. As an initial result, we have reduced finished inventories by 10%, with the potential of greater reductions in the near future. Our manufacturing and production scheduling are now more closely coordinated with sales needs than ever before. And our field warehouses are stocked more intelligently, enabling us to serve our customers better. Fundamentally, the National 304 has given us faster and more accurate control over sales efforts, production, inventory, credit, and customer billing. It has sharpened management reflexes, enabled us to harness data in time to be used most profitably, and meets our demands for the factual data necessary to make management decisions in time. Leading manufacturer of wax polishes and other fine products for home, industry, and agriculture. The National Cash Register Company, Dayton 9, Ohio. 1,039 offices in 121 countries, 77 years of helping business save money. Computers and Automation for July, 1961. To be most effective at this stage of our installation progress, it is difficult to assign a definite money value to all these advantages. However, we know their value represents a highly profitable return on our investment. President S.C. Johnson & Son Incorporated. 5. Readers and Editor S Forum. Front cover, memory for a pneumatic digital computer. The front cover shows a laboratory prototype of a component for a pneumatic digital computer, under design by Kierfot Division, General Precision Incorporated. Little Falls, NJ. This component contains two BIST-able elements or flip-flops and has the capacity for 4 more. The piping consists of holes drilled in the layers. Connections to the flip-flops are made through the screw holes at the top and bottom. The component is created by clamping the layers together. Each chamber containing a little ball has 2 inlets and 2 outlets for gas, either under high pressure or low pressure. Pulses of pressure operate the pneumatic components. The entire size of the prototype component shown is a little over an inch long and a little over half an inch thick. Much smaller sizes are possible. An event UAL component density is indicated of 2,000 to 4,000 BIST-able elements per cubic inch. Under these conditions, a medium-sized general-purpose digital computer will occupy a slab approximately 5 by 2 inches square and 1 inch thick. Operating speed indicated is in the range of 10 to 100 kilocycles. Operating temperature can be well over 1000 F. All digital operations can be considered to be combinations of 3 basic functions: counting, switch, ing, also called logic and memory, and these 3 basic functions can all be represented with pneumatic components. In addition, signal conversion is possible from pneumatic to electronic, for example, by sensing electrically the position of the little metal balls, and from electronic to pneumatic, for example, by electro-magnetic impulsing of the little balls. Compute.Rs in Nuclear Engineering. Dr. Jan Paul. Nuclear Consultant. 2617, Lynn Street, Bakersfield, California. There are a number of individual applications for computers in nuclear engineering. Some of the more important are data logging, alarm scanning, online computation, sequencing, data reduction, automatic control, and reactor monitoring. All are important. ing and timing equipment, and input-output equipment for the computers. The basic principle behind the system is quite simple: any kind of break or fault will cause an increase in the level of radioactivity in the reactor cooling system. It is essential that this increase be detected before it can become harmful to personnel or equipment. The radiation detectors in the system are placed in the cooling channels and connected to the binary counters, which in turn are scanned continuously by the computers. The computers use the data obtained to calculate a radioactivity level for EAHCHN, L, and compare it against a pre-determined limit. If the calculated level thus obtained exceeds the limit, alarm and warning devices are automatically activated. The computers are operated in parallel to assure uninterrupted protection. Both machines therefore receive all input data and make all calculations. However, only one operates the automatic typewriters and alarm devices. They are systemed, however, so that should either computer stop, break down, or make an error, the remaining machine takes over all output devices. Each computer checks itself once a minute. Of the 7 typewriters in the system, 5 print output radio activity values. One does nothing but indicate equipment failure, while the remaining machine logs reference values. This particular reactor installation has 1148 cooling system channels, which, for the purpose of scanning, are divided into 287 groups of 4. 12 channels are scanned per minute, so that a total scanning cycle takes 24 minutes. In the event of an above normal reading, all 4 channels in the group are switched to a fine scanning system through which the computers can calculate a normalized level for each separate channel. If any of these exceed normal, warning devices go into action. A careful evaluation of this, and similar computer monitoring systems indicates that these systems make possible the continuous calculating of radioactivity levels over an extensive channeling system with a maximum reliability factor and a minimum of alarm error. The safety factor for both personnel and equipment is also greatly increased. But perhaps the most important single application is computers and armaments. underscore 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 in underscore c act cr underscore mknitkring underscore for underscore in underscore such underscore an underscore application t dash dash dot rw dash s possible for the computer to monitor radioactivity if rom car iu groom in the reactor through a hookup with the cooling Arlington, NJ and heat transfer systems. To the editor. Perhaps one of the most interesting computer with reference to your article armaments and applications is at the Electricité de France Power Computer people in the May issue, I believe you. Plant near Chinon, France. The installation is of leave out of account a rather important fact. This is particular interest in a discussion of applications, that every arms race recorded in history has resulted. Because its computer system, while primarily for in a war. There are formidable odds, therefore, that monitoring actually combines a number of important the present arms race WI-11 result in war. Therefore, uses. The system consists of two RW300 computers, the major task of patriotic computer people, other 7 automatic typewriters, a paper tape punch and scientists, and in fact everybody in the United States. Reader, radiation detectors, binary counters, sequin, please turn to page 22. 6 computers and automation for July, 1961. Schnee. Dell. RC. 60. 53. Schnee. East. SPR. On. Schnee. SYSL. Sir. ST. Ter. SCHWC. COL. Dell. 21. Shell C. COL. BAL. Wes. Eng. Sim. GP. And. Slash. CM. COR. IRI. Spark. RC. FLA. 52. Stag. SESI. COR. Slash J. Turn. M. MB. Out. Art. Stua. Lee. Tur. San. Still. Stoyan. Gas. S. Pet. SPE. Leu. Tolpe. Thel. On. Worley. De backslash. Flig. 305. Uni. Eng. Mal. YOT. May. Lie. 707. Warn. Tim. Seer. Tral. Timel. Of. Pro. Mat. As. As. White. Ken. Frat. Phi. Com. And. Ord. Rye. And. Tem. Com. FC. Box. Uju. EP. 40E. EO. High. Data. City. / University. PT of. 4 of. PT of. LAI. T60. IM. Turai. Post. Sept. In of. Lysis. Volume, I-59. Ropey. C of. 59. LE. Rotor. Ear. Easy. Bowery. Elec. Shell. Po. LMP. SPE. Oved. RAM. RSA. Adal. EB. Turns. 2500. If/. University. LE. Ma. Null. DC. RTNS. 55. LLLS. PPA. .lyst. US. LP. City. 1, and IEN. SOC. Thursday, IORC. Janev. Lpter. MS. OK. Re. 1 and. Ago. S/. Rob. Ions. NGR. Pa. DL. Itate. Logi. 961. For men of vision. Waiting for you at Burroughs Corporation are some of the industry's most challenging and rewarding career opportunities. An extensive and purposeful research and development program has spurred the introduction of several major systems this year, including the pace-setting new B5000, the first computer specifically designed to implement problem-oriented languages. There are more to come. A planned program of future releases will ensure continuing growth. Opportunities. Substantial opportunities now await qualified personnel in the following positions. Special computer representatives, to promote the sale of this advanced data processing equipment, working with experienced account representatives. Opportunities to advance are wide open because of Burroughs' practice of developing management personnel from within. Salary plus override will be attractive to experienced computer sales representatives. Sales technical representatives, to assist sales representatives in technical aspects of sales presentations and guide installations of systems. You will receive progressively more challenging assignments in either scientific or business data processing. You'll qualify with strong magnetic tape installation experience or sound punch card systems background, and receive a salary commensurate with experience. Openings are available in major cities throughout the US. Call the manager of our office near you, or write in confidence to LD Staubach, Director of Marketing Placement, Burroughs Corporation, Detroit 32, Michigan. Burroughs TM. Burroughs. All qualified applicants will RFPIV, consideration for employment. Without regard to RAC, CNEU, color or national origin. Corporation. Computers and Automation for July, 1961-7. Open Shop Programming at Rocketdyne. Speeds Research and Production. DJ Brahim. General Supervisor, P. Programming. Rocketdyne, a division of North American Aviation Incorporated. Canoga Park, California. Engineers writing programs for themselves. Computer usage is high, engineering problems are solved quickly and completely, and design and production benefit accordingly, with Open Shop programming of scientific problems at this division. Some 400 of our engineers, at least one in every engineering group, write computer programs for themselves and their fellow engineers by using a formula translator which enables them to address the computer in more or less familiar language. A monitor SYS TEM we have coupled to the computer allows us to run a tremendous volume and variety of their problems quickly and efficiently. Thus, we have placed in the hands of our creative engineers a super slide rule. Fully as important, our engineers are in direct contact with our computers, an IBM 709 and a 7090. Thus they are familiar with what these machines can do and tend to program onto them the total problem, not just a piece of it at a time. Expediting solutions. This, too, expedites the solutions to design problems and, eventually, speeds production itself. In rocketry, of course, problems that stand in line awaiting solution quickly become so dated they aren't worth solving. We are convinced that closed shop programming, in which our engineers would bring their problems to full-time programmers, would tend to create bottlenecks. For one thing, an engineer can write his own program in 1/4 as long as it would take him to give it to a programmer and get it checked out. Even more important is the problem of communication. For example, a programmer might think he understood a problem when actually he did not. Reprogramming then would become necessary. This is understandable, because no one person can master the fields of stress, heat flow, aeronautics, etc., and the other incredibly diverse uses for which our computers must be programmed. Even when a programmer understands the field generally, he often lacks the feel for a specific problem which the engineer himself has. In addition, making the computer available to the engineer, either through his own ability to program or that of a fellow worker, encourages him to use it. Encourages the let's try it attitude so valuable in creative engineering. Shortening of training time. Also, through the use of Fortran, IBM stand-on formula translator which implements our open AutoIt shop, the try-and-me time for a programmer has been cut from 60 hours to just 20 hours. And, our engineers can and do write usable programs as soon as they've completed their 20-hour course. Without Fortran, a graduate of the 60-hour course used to spend 6 to 8 months learning to write sophisticated programs. Thus, the goal of our open shop is not to produce a relatively few, highly sophisticated programs. It is to encourage engineers to solve the largest number of problems via workable computer programs, with the end result of getting the best product built, most economically, in the shortest possible time. While this has always been a desirable goal throughout industry generally, it is particularly pertinent to the missile industry. Any discussion of the missile race is superfluous, of course. Even the most casual scanner of headlines knows we are in it, and maybe believe that the very survival of the United States may hinge upon the outcome. Rocketdyne's background. Rocketdyne's contribution toward high-thrust rocket engines and advanced forms of propulsion for use in space date back to 1946. Missiles and research vehicles powered by RN. Guinness include the Army Redstone, medium-range missile, the Air Force Thor and Army Jupiter, first in intermediate-range ballistic missiles, the Air Force Atlas, our nation's first intercontinental ballistic missile, and many of our nation's space probes, including the Redstone-boosted Explorer satellites in 1958, advanced space probes by the Air Force and Army, the Discoverer series of polar satellites, etc. Our main offices, plant, and data processing center are located at Canoga Park, near Los Angeles, California. We also have plants at Neosho, Missouri, and McGregor, Texas, and a propulsion field laboratory for research, development, and production testing in the Santa Susana Mountains, near Canoga Park. Our two IBM 709s are in operation 24 hours a day, 7 days a week. About 90% of their usage is scientific. Of this, about 3/4 is for Rocket Dyne and about 1/4 for Atomics International, another division of North American Aviation. In addition, our data communications system enables us to handle overflow work from North American in Los Angeles. Nature of computing load. Our computing includes quite a bit of test data reduction, performance analysis programs, trajectory computers and automation for July 1961. Rex. Put. Bensel. Lisi. Ton. Cali. State. Jesus. Near. Tem. 1011. Henged. Cole. Sean. Ne / Ods. Dicoslo. Cor. Tem. Drove. Anna. Shell. Cabe. Ver. Duke. PRGL. Of. Tex. Com. Aaron. Lant. Folk. Anti. Tra. Fagan. ICC. Late. 99. 59. /LV. DIR. VVH. Fetal. Errol. Ton. Apple. Eng. Turn. Cod. Dad. N. Fleming. N101. Me. Still. Phones. Ins. Ha. Free Fi. PRG. N. ANC. De. 57. Frets. PRG. Hot. 152. 47. Gillis. AP. Slash. Jur. N. Slash. Lizzle. Vice. N. TIDI. Goer. Vi. 32C. Slash. Hall. BN. CH. Com. Electon. Stevens. Mock. /35. /37. Texas. Laredo. JFP slash. RGMR. PRGMR. ABLP. LP slash. RGMR. /25. LP slash. RGMG. BP slash. East. LP slash. Lin ST. LMP. Int and. Slash. RGMG. List. RPS. New. INST. US. Ward. Ivark. 31. Ping. Chell. University. Department. S on. Toll. Min. Abe. 52. DIV. Lowers. TCMS. Leans. ORP. 1684. RC. 53. PLE. Holiday. EAT. 1961. Programs, reliability studies, etc. We process more than 200 jobs a day on the 709s. As indicated, a large percentage of these are from the 400 engineer programmers we have encouraged to use the machines. It is necessary, of course, to handle these jobs quickly and efficiently, or we lose the value of open shop. As set up, if an engineer gets a routine problem to us by late afternoon, the results are on his desk early. The following morning, if he gets it to us in the morning, he has his results by afternoon. And, on a priority order, we give him fast enough service so he can have 2 or 3 shots at the 709s on the same day. Our goal is a turnaround time of 3 hours. On routine work, exclusive of key punching, and 2 hours for a priority job. Rush work, such as accept and tests, is handled much more rapidly, of course. 10-minute service is about average. The monitor system. The monitor system, mentioned earlier, and careful channeling of incoming work, enable us to process our high volume quickly and efficiently. VVE call the monitor our load and go system. Developed here in 1958, it was subsequently used by IBLVI as the basis for the share standard SYS. TEM, now widely used with Fortran. The monitor enables us to group jobs efficiently on the same tape, with the machine doing most of the controlling. When an engineer has completed a program, he sends his data sheet to data processing in a special gray envelope, used only by DP. The data sheet may be accompanied by a program deck, or we may already have the deck on file. A receiving clerk checks the sheet for legibility, then routes it to an IBLVI card punch operator, who produces a data deck from it. Next stop is the setup section, where the deck is checked and placed in back of the proper program deck. The program and setup decks are sent to a dispatcher who assigns several jobs to each tape, in most cases, and sends them into the 709 room. There, the cards are loaded onto one of 2 card-to-tape conversion units, and the information from them is reproduced on magnetic tape. The tape then goes to whichever of the 709s is open. The operator loads it onto a tape unit, starts the program and just monitors the time on each job. If there were any errors in programming, the 709 prints out a notice and the specific program is shunted off the machine. When all the jobs on the input tape have been run, the operator removes the computed data on just one output tape, and places it on an offline tape to 720 printer to produce a hard copy of the results at 500 lines a minute. When the program calls for it, the 709 also produces a second output tape, from which a deck of output cards is punched. The computed data sheets, and any output cards, go into a gray envelope, and back to the originator by special courier. Elimination of duplication. One of the traditional problems of the open shop is duplication of effort. To eliminate this as much as possible, we have published all programs devised here, and distributed them through North American aviation. We do not envision the day when every engineer will write programs, or when full-time programmers will be eliminated, of course. We still have the equivalent of 50 of them busily at work on a variety of jobs, including teaching Fortran, debugging programs, handling complex programming, and programming commercial work via Comfort, our version of commercial Fortran. But, we do believe that the open shop educates our engineers in the maximum use of the computing tools available to them, and encourages them to use these tools properly, not on a hit or miss basis. The result is that more programs are written, more problems are solved, and more products are built faster, better and more economically. This, of course, is the major goal of all of Rocketdyne. Who's who in the computer field? Name. Please print. Year entered the computer field. From time to time we bring up to date our who's who in the computer field. We are currently asking all computer people to fill in the following who's who entry form, and send it to us for their free listing in the who's who that we publish from time to time in Computers and Automation \VE. Are often asked questions about computer people, and if we have up-to-date information in our file, we can answer those questions. If you are interested in the computer field, please fill in and send us the following who's who entry form. To avoid tearing the magazine, the form may be copied on any piece of paper. Your address, your organization, ITS address, \our title, your main computer interests, applications, business, construction, design, electronics, logic, LVI thematics, programming, sales, other, specify, year of birth, college or last school, computers and automation for July 1961, occupation, anything else, publications, distinct ions, etc. When you have filled in this entry form, please send it to who's \VHO editor, computers and automation, 815 Washington Street, Newtonville, Go, Mass. Automated Teaching. E.F. Cooley, Director of Methods Research, The Prudential Inns Co. of America, Newark, I.N.J. Based on a talk given at a Person F Management Conference in Mobile, Ala, February 1961. Automated teaching is an important subject. It is important because the new methods currently being developed offer real hope of reducing waste, and waste reduction is always important. The waste in this case is the waste of time of students and trainees, and this waste means waste of the money of schools and of employers. The purpose of this report is to give a general survey in elementary terms. Hazards in ordinary class training. Training is usually done in classes of 15 to 25 PEO. PLE. Then ever you have a group that big in any activity, there is bound to be compromise of some kind. The place, the time, the instructor, all are compromises to some extent. A class as it is usually run means more compromise. Some students can go faster than others, and often a class of trainees is slow to the pace of the slowest. Sometimes 2 or 3 individuals dominate the class, ask and answer all the questions. The instructor never knows if the other students are learning until he sees the results of the first test. Now there are tests and tests. At best, they cover only a sample of the facts the trainees should have learned. So a test may in some cases show how much a student has learned, and in other cases it will not. There are other hazards which prevent rapid and thorough learning. One of the most common is a poorly chosen instructor, one who does more to confuse than to clarify the object. Instructors are chosen very often because they know the subject, without regard for whether they have any ability to explain and Teach it? I believe that a teacher must know his subject, but also that knowing the subject does not necessarily make a good teacher. Private tutoring. Perhaps some of you have had the experience of receiving private tutoring from a good tutor, one who really knows his subject and knows how to teach. Then, you were the sole object of his attention, and every question he asked was yours to answer. The good tutor soon knew whether you had a good grasp of the subject or not, and developed his remarks and questions accordingly. He adjusted his presentation so that you were able to learn at your own pace. You were neither held back by other students who learned more slowly nor pressed to go faster than you could, by the progress of more advanced students in your class. Now I will not go so far as to claim that any teaching machine is as good as a good tutor. But for some subjects, a well-planned text presented in a good machine approaches the situation of having a private tutor. Especially is this true when the students are well motivated, are really anxious to learn. Certainly this is the situation in a big company when we carefully choose candidates for a new endeavor in the organization, and they know that a raise or promotion depends on how quickly they learn the new work and become productive on it. Essential features of the teaching machine idea. The terms, teaching machine, automated learning, and program text, need some clarification. At first it is easy to think that the machine is the all-important feature of the new technique. However, this is not the case, in my opinion. A mechanical device may be very helpful, but it is not the necessary element. The essential features are two. First in importance is the carefully developed sequence of questions or statements called the program. The learner must make a definite response to each step before proceeding to the next. Second is the fact that the learner is told immediately whether his answer is right or wrong. There is evidence that the most effective program is one to which the learner responds correctly at every step. The reward of being right constitutes reinforcement of the fact in his mind. Since the steps or increments of knowledge are small and many, each requiring individual response, there is opportunity for almost continuous reinforcement. Programs. An incremental presentation, properly constructed, leads to more complete learning. It brings the student along to a gradual mastery of the subject as he progresses from simple to increasingly difficult increments. Meticulous text preparation leaves no gaps or ambiguities to impede understanding. This sort of text called a program may be presented in book form or by certain types of mechanical devices. But in either case, the important thing is the preparation of the text, however it may be presented. Scrambled book approach. 1D like now to describe some of the forms of presentation. First, let's consider the scrambled book. Let us consider a few pages from a book called The Arith Computers and AutoIt for July, 1961. Mid. Shin. Tel. Sept. Adia. Dal. N. Ch. Lanel. Mal. Hill. Sept. Tel. Bas. Sept. 4. Cal. Ran. W. Sept. CR1. Th. Ba. Sept. Fur. BIL. CA. 31. Sept. 2. Custy. Ifacaf. Shan. Sistel. Trayer. SALL. Ins. Math. Rit. The. 315L. Work. Hand. Istic. Co. Out. Berg. And. R of. Slain. OM. Dickel. Bio. DR. 1 of. Asian. Van. Ian. 836. Isco. No. 1.aiog. Asian. Iona I. Uto. Lavia. Sion. Uwage. Dun. 1961. Medic of Computers, prepared by Mr. Norman Crowder for use in training programmers at the SYS. Thames Development Corporation, and published by Doubleday. This book is intended as the student's first introduction to this subject, not an auxiliary to other texts which have to be read first. The purpose of the book is to provide the reader with a useful knowledge of the number systems used in electronic computers. The presentation is as nearly as possible a set of alternative conversations between a teacher and his pupil. But it is not an ordinary book, although the pages are numbered in the usual way, they are not read consecutively. The book offers information in rather small units, and tests the reader's understanding by means of multiple choice questions, and each answer is tagged with a page number. The reader must answer the question in order to proceed further in the book. After the reader chooses an answer, he goes to the page corresponding to the answer he chose, and there finds out if he was right or wrong. A wrong answer leads to more discussion of the same point of information and refers him back to make another choice. A right answer leads the student to the next unit of information and the next question. This may be enough explanation to show how the scrambled book or tutor text, as Mr. Crowder calls it, may be used. Besides the book, a machine has been designed to take the place of the book. IT is a projector for 35mm film. Each page goes on a GLE frame and may be projected on the screen. A single roll of film will hold 10,000 frames or pages, which is the equivalent of several books. The book, for instance, has 472 pages and is about 1.5 inches thick. So 10,000 pages would be 4 feet high. When you use the machine and wish to go to a certain page, you merely punch out the page number in the keyboard, hit the motor bar, and the machine spins the film to the desired page. You can say, I suppose, that the machine is just a very expensive page turner. But you must admit that it is a very convenient one. It is also capable of turning itself into a moving picture projector and of accumulating totals of right answers on first attempt or of total time for a certain sequence, if such scores are desired. There is no denying that the machine adds cost to this method of training. But it also adds glamour and makes the process more interesting. I might add that Mr. Crowder's employer, US Industries Incorporated, is now offering a less expensive machine, a sort of compact model. This therefore is an illustration of one of the two main schools of thought in the field of mechanized Training. This was the multiple choice method, and clearly it is much like multiple choice tests which have been in use for years. Skinner approach. The rival method is often called the Skinner AP approach after the well-known psychologist, Dr. B.F. Skinner of Harvard. Skinner insists that the student construct an answer for each question, and claims that this is much more effective as a learning process than the multiple choice method. Computers and Automation for July, 1961. It appears that more machines have been designed as copies or revised versions of the original Skinner machine than have been made to implement the LVIL multiple choice approach. A good example of a Skinner type machine is the Didac 501, made by Ream Caliphone Corporation, Los Angeles 28, California. For use in this machine, incomplete sentences and answers are printed successively on standard letter size paper. The sentence to be completed is spaced so that it alone shows in the aperture on the face of the machine. After completing the fill-in, the student turns the knob, which advances the sheet bringing the answer into view while his own answer is still visible. Thus, he knows immediately whether his answer is right or wrong. There are strong partisans for each method and the experts are divided. The General Electronics Corporation of Philadelphia have experimented with various devices and have favored the multiple choice AP approach. Their vice president, Dr. Robert Roop, now says that he is planning a combination approach. This seems to me to be a very sensible thing to do. Dr. Roop's most recent device uses what he calls the TAG, Teaching and Grading, system. For this system, the program is printed in book form and the student records his choice of answers by perforating the answer sheet with ballpoint pen stylus. The answer sheet is clamped in position over a template with shallow holes for wrong choices and deeper holes for right answers. As the student pushes the stylus through the sheet, he knows at once if his answer is right or wrong by whether the stylus is stopped or penetrates deeply. The type of hole in the answer sheet is a permanent record of his choices. Room is provided for fill-in answers at the top of the sheet. Here the device does not contribute anything except as a sheet holder. The correct answers are to be found on the next page of the text. Programming. Dr. Roop is planning a course in programming techniques, programming for teaching devices, that is. The need for good programs is now the greatest obstacle to the expansion of the use of teaching devices. The need for well-constructed and tested program texts to produce a good program is usually thought to require a person trained in psychology. But if the knowledge of how to produce a good program can be conveyed to others so that any of us, after special training, can write effective programs, a great step forward will have been taken. 1/uke of the experimental work that has been done has pertained to teaching at the elementary or SEC Andre school level. Some important research has been done in the Roanoke, Virginia, school system. The most notable result seems to be their experience in teaching algebra to 9th graders. Those using the automated course finished a year's course in one semester, and also stood high in examinations given on a national basis, indicating that their grasp was better than average even though only half the time was spent. 11. Programmed books. At collegiate school in New York City, The Count. Tries oldest private school, a great deal of experimental work has been done over the past 3 years. The use of incremental texts has proved very successful, both with outstanding students who can forge ahead at their own pace and for our talented students who need to spend more than average time. It is of interest to note that at collegiate school the mechanical devices have been largely discarded. They feel that the various forms of printed texts in incremental form are just as effective without the machine. In line with this comment, mention should be made of an experimental text recently published by Har. C. Alright, Brace, called English 2600. This is a text in grammar and English usage. It is a paper-covered book about an inch thick and each page is divided into 6 sections. A section on page 1 contains a statement with a blank to be filled. The student writes his answer and turns to page 3. There he finds the correct answer and another completion statement in the corresponding section of the page. He turns to page 5 and again finds the correct fill-in and another question. Thus, he proceeds along one band of the book, right through to the end. Then he starts through again on the next band, repeating until he has covered all the odd pages. Then he starts on the bands on the even pages. The reason for the number 2600 is that there are about 2600 programmed steps in the book. This appeals to me as one of the simplest systems I have seen. Programmed machines. The other end of the scale is the experiment at the Systems Development Corporation, where an experimental project is using an entire electronic computer hooked up with a random access slide projector of their own design. Using this arrangement, they can carry out many kinds of experiments, including such possibilities as making the successive frames of text easier when the student has not done well, all this under the control of the computer. This leads to conjecture as to whether computers may not be used to tailor, automatically, the text to the individual needs of a whole roomful of students. Automated teaching of computer programming. 1/11 Why main interest is the use of automated teaching of technical subjects, in particular, computer programming. I know of research being carried out by both International Business Machines Corp and Radio Corp of America in using incremental learning techniques for training, but in neither case do their own computers seem to have any active function in training. RCA has quite an enthusiast for the Skinner approach in the person of Lon Grace, who has designed MD built a machine which he is now using in experimental teaching of their scientific interpreter for the RCA 501. He is making some preparations to leach COBOL, the common business-oriented language, which is expected to be the universal system. 12. Or describing a procedure so it can be put on any computer. IBM has apparently had good results with the research projects in the subject which they have carried out. Their first and main use so far has been in training customer engineers, where early results show that the job can be done more thoroughly and with less total time spent by the students when a program text is used. They have also tried out the technique in teaching classes in computer programming for the Type 7070 machine. Here, with 70 PLE in 6 classes using the new technique, and with 42 people in 2 classes as a control group not using the new technique, they report that the experimental group averaged 95% in an exam given after 11 hours of training, while the control group averaged 86% after 15 hours of training. They consider the experiment a success so far, but will not be ready to report any final results for at least another 6 months. The kind of action I hope IBLY1 will take is to furnish tested text material to their customers for teaching all phases of programming. I would hope that this material would be made available in a form which can be used with one of the simple teaching machines. If, in our company, we are able to assign a new recruit to be trained in computer programming, and if we can let him train himself at his own pace, without waiting for a class, and without being held back by a poor instructor or slower to earn students, our present cost of training will be materially reduced. We have a large staff on this work and a high turnover rate, so the cost of training is a considerable item. The cost of sending people to class is easy to measure, but the cost of slow production while they are learning on the job from other more experienced people is very difficult to assess. As we get more and more into technical methods of operation, the need to modernize our training methods becomes increasingly important. For background knowledge on this subject, let me refer you to Teaching Machines and Programmed Learning by A. Lumsdaine and Robert Glazer. Published by the Department of Audiovisual Instruction, National Education Association, Ashington, D.C., 1960, Library Congress Card #60-15721, 724 pages, a combination of 47 useful and / or important articles, with supplementary information. Importance. In my opinion, the teaching machine, defined broadly enough to include the whole field of program texts and incremental learning, is not just a fad and a passing fancy of the psychologists. Rather, it is an important development in which we should all take an interest and with which we must become intimately acquainted. Neither in schools where our children's time is more and more at a premium, nor in industry and clerical activities can we afford to waste the centuries of time that are going down the drain with today's training methods. Computers and Automation for July, 1961. Uni. Proc. CNT. The. Wow. SYSTE. Gave. Fewer. The. Way. Lem. Men. Shul. BROL. Agar. 1 \. Fessy. Matty. FM. Wid. Desil. Libric. Hap. Naughty. I \I. Clal. OpCL. Lion. Tiv. Titat. Lyru. Pain. Pun. Intel. In and med, men, and r, bd, cons, we are, l, bet, the one, a bowl, hap, dam, dean, fast, a p, allo, free, Poundry, and BL of TL, Dale, Stars, Mon, etsp, Com, LRY, B, and TLIS, LTHY, SCL, NS, we, listen, hin, ogi, Eichel, fr, OS, X, ibl, Y, B, that, UD, S2, head, eat, lies, up, audi, keys, I2, con, han, EA, DIP, SYS, Laney, and IDAS, RA, in, .t is, Tikal, Pro, Fed, Lara, by, her, .ints, the, and, .her, ifl, RAF, we, shin, and, in, the, 1961. The Trouble with Commercial Compilers. John H. Hughes. Assistant Vice President, Data Processing. American Mutual Liability Ins. Co. Wakefield, Mass. A number of artificial languages, technically called source languages, have been designed to make it easy to describe business processes in such a way that the description is susceptible to computer translation into the computer's instruction language, technically called the object language. Some of the source languages bear the names FLOWLVIATIC, COM, TRAN, FACT, COBOL. The computer translation takes place under the control of a program called a compiler. These artificial languages have one thing in common. They all make use of English words and sentences. It is my contention that this is not, as is often claimed, their principal virtue. On the contrary, it my thesis that the chief weakness of commercial English language programming systems is, in fact, their empted use of English. Should you write programs in English? Let us consider for a moment the principal claimed advantage of English language for source programs. English is spoken, written, and understood by practically everyone who matters to the manufacturers of large-scale computers. So, computer marketers would have us believe it is unnecessary for the user of a large-scale computer, with its associated English language compiler, to learn a new programming language. He can write his programs in good old familiar English. In fact, the English understood by computers is not the English spoken by you and me. It is comprehensible to us because it uses some of the same words and some of the same grammatical structures. But we cannot claim to have a speaking knowledge of this language until we have learned its strict ions. Here a conscious effort of learning is required, just as a conscious effort is required to learn, for example, that other artificial segment of English called Basic English, the simplified English using a basic 850 words devised by C.K. Ogden, of Oxford University. In learning Basic English, a foreigner has a marked advantage over a native English-speaking person, in that he is never tempted to use English words that lie outside the permissible vocabulary, because he does not know them. But if you or I try to speak Basic English, we must make a constant effort to avoid words which lie outside its vocabulary but which are temptingly convenient, concise, and precise. Computer English, then, does require learning. It is Simply not true that an untrained person can sit right down and start programming a large-scale computer by using an English source language. Redundancy of English. Another feature of spoken or written English is its high degree of redundancy. Of the possible combinations of letters or sounds, only a very small computers a 1/D automation for J. Euler, 1961. Proportion constitute allowable combinations. 4. This reason misspellings and mispronunciations, while they may cause an emotional reaction detrimental to communication, present no serious technical block. UCNRD and D understand attendance return ek ths wound wf. Bit as much accuracy as th previous sense. This is because you have an ability as yet scarcely within the reach of computer programs, to recognize common phrase and spelling patterns and to compensate for the distortions that may be present. To program a computer to be insensitive to bad grammar and spelling is conceptually possible, but probably a waste of time. So, computer English loses the advantage of ordinary English's redundancy, i.e. the ability to communicate reliably despite noisy channels, while retaining its disadvantage, lack of the conciseness which could be achieved if the size of the universe of possible messages were restricted. Looking at the matter of language from the point of view of the computer programmer, then, computer English fails on two counts. It is difficult to write precisely enough for comprehension by the translator, compiler, program, and it takes too much writing to express a simple command. Length of program. The program, once reduced to computer English, must be transferred to a machine-readable form, cards, paper tape, or magnetic tape, for the translation program to operate on it. Again, the same failings plague us. The great length of the source program increases the probability of transcription error, while the requirement for precision makes such errors costly. The illusions of upper echelons of management, with the limitations I have described so hampering its usefulness and efficiency as a source language. How has English language programming, computer English, reached the position of importance it now occupies in programming technology? Sad to say, I believe this has happened because most of the people who have to make decisions about the purchase of computer equipment for commercial use do not have the faintest idea what they are doing. This is because the computer business is so young that hardly anyone has yet had time to move through a work experience of practical programming into a position of executive responsibility. To them, the illusion that by obtaining a computer with an associated English language compiler they can avoid selling their company down the river to a bunch of technicians has enormous sales appeal. So they decide to go ahead, using Fact or Flowmatic or Comtran or COBOL. And the programmers suffer. Those who are of necessity trained in machine, or Ngar machine, language are agonizingly aware of the sacrifices il progral efficiency. 13. That are made to achieve a compiler that can be implemented. Those who write in the source language soon become aware of the sacrifices in programming efficiency that are made to achieve a language which members of the upper management echelons can read and understand. Do these members of the upper management echelons really gain anything from the use of English source programs? I doubt it very much. The source programs are still written in a degree of detail That should be of no concern to upper management. The essential facts about a system must still be presented to upper management in broad brush terms, having little relationship with the computer English of the source program. How about the immediate supervisor of a programming group? If he knows his business thoroughly, the English language is likely to irritate him by its inefficiency. He may approve the use of an English language compiler because it allows him to get working programs written by programmers whose machine language efforts might well be no more efficient, or because it lessens somewhat the need for programmers with the rare turn of mind and personality that can enjoy making a computer sit up and talk. He is unlikely to be happy with the sacrifices that must be made, and he will recognize that the power of such a compiler arises not of but in spite of its use of English as a source language. Progress by abandoning computer English. The fact compiler of Computer Sciences Corporation, which is being implemented for the Honeywell 800 computer, overcomes partially the disadvantages of the English language by abandoning it for the expression of the input editing and report writing requirements of a system. The next logical step, I believe, is to abandon it in favor of a less redundant code for the intermediate phases of the system. I should like to propose here, then, that the efforts of the applied programming groups now working on English compilers for a new language designed to have the advantages of English without its disadvantages. For example, the new language should avoid the use of unnecessary connectives, those implied by verbs. It should have a vocabulary of verb abbreviations easy to learn but not readily confused with their true English counterparts. The vocabulary should include verb abbreviations for common data processing actions for which no single verb today exists. 2. Satisfy the demand, such as it is, for program records. In computer English, the implementation of the new language translator could include a retro-translation into unabbreviated regular English. No sacrifice of real advantages. The following very real advantages that English language and other compilers have need not be sacrificed till the implementation of this new compiler. 2. F. It is generally true that English language compilers require the programmer to describe the file organization or layout in a fairly concise language defined for the purpose. At the time of file description, the correspondence between fields in the file and their English names as used by the programmer in his English language programming is established. In naming the fields, the programmer can decide for himself whether he wishes to use full names or abbreviations. The important advantage gained is that the file description is available to the compiler during compilation of any run using the given file. The programmer does not have to consider the layout in detail and can refer to fields by name with the assurance that generators within the compiler framework will provide addressing and masking as required. There is nothing in this process that is peculiar to an English language compiler. Although the problems of implementing an English language compiler gave impetus to its invention. 2. The vocabulary of English language compilers can include verbs representing operations which involve many machine instructions, example get. Next, a file item. That get covers a multitude of sins. This is merely to say that the commands of the English source language are Macro instructions, but macro instructions are by no means peculiar to English language. Compilers. 3. The fairly concise non-redundant methods used for expressing input and output edit require ments which some English language compilers resort to can and should be retained. Finally, a B.useness-oriented compiler should permit facile inclusion of machine, or near-machine, code. There will continue to exist functions which are practically impossible to generalize efficiently. Table storage is an outstanding example. Most tables can be stored far more efficiently if the word structure of the particular machine is understood and taken advantage of, and the increase in efficiency may amount to a factor of 5. The title of this paper is, To Catch Your Eye, the Trouble with Commercial Compilers. The trouble is not, as I think you can see, a basic one. But let's stop deceiving ourselves that the English language has any virtue of its own as a language for writing source programs, and let us concentrate on designing a source language whose redundancy is only as great as may be helpful in making it easy to learn. Compiler, a computer program which directs a computer to translate a program written in a problem. 9. Rented or process-oriented source language, the source program, into a program recorded in machine language, the object program. Programming system, a programming language plus the compiler or assembler needed to translate the source program into machine language. Redundant, a message is redundant if it contains more information than is needed for the recipient to distinguish which member of the universe of possible messages is intended. Any message which can be shortened without loss of intelligibility is redundant. Computers and Automation for July, 1961. T. Loss. Info. Men. Tem. Will. Asia. Chal. Set. Shan. Un. Hun. Dict. Is TB. Able. Pud. C. Su. R. Tem. Of TL. INTE. Of H. Elec. Shan. O tilt. 1. WHI4. Nat. Tien. Do. Tiv. Up F. Bina. Allen. T. Char. Part. Tour. CN. HNH. Cons. Thiel. Alt. Perl. Of 1. T. The I. Prow. Of TL. Lnkre. Sour. Dikr. Atur. Hum. Clan. Route. More. Hum. Thin. Spiel. Com. Them. Ibera. IE4. Build. Wyker. Even. Chords. Louse. Antify. T and. Lidu. Blems. Insys. Wipe. Will. And the. Mess. Lines. Elec. DNGLY. F the. Step. Ilting. Irva. Iving. Tier. St. It. R. Nant. Thing. Irva. 111 inches. CS. It. Any. EAP. How. Elval. Com. Roworld. Ian. Regent. Ships. Hings. Clear. Pilot. Obel. Lmic. The. Rutary. Antac. Glacial. Edic. And. Will. TB. Italy. Rich. Leading. His. 1961. The Coining Technological Society. Dr. Simon Ramo. Executive Vice President. Thompson Ramo Wooldridge Incorporated. Los Angeles, California. Based on an address delivered at the University of California, Los Angeles, May 1, 1961. We are all aware today that we are in rapid transition to a new, highly technological society. The POS. Cibilities that will unfold and the PR0 blems that will arise in this new age ahead will present many challenges to the scientist and engineer. However, these challenges will not begin to compare with the new opportunities that scientific advance will open up to society as a whole. The new technological society. What will the new technological society be like? There is already a gross imbalance between technological and sociological progress. In view of this, will the transition to the new society be orderly or chaotic? Civilization will have to absorb the impact of science and technology. We do not really have a take it or leave it choice. For one thing, the increasingly fast-paced, complex, and interacting world, with its rapidly expanding population, urgently requires solutions to the problems of its physical operations of production, communication, transportation, and resources control and distribution. Because technological creativity and scientific advance are able to do so, they are furnishing the answers to these kinds 01 problems. In other words, on the material front, a match between the need for solutions and the ability to formulate solutions exists, so science and society are through with their courtship and are now getting married. Will it be wedded bliss, with the offspring sources of pride and joy, or will it be a shaky, unstable partnership? Technology has clearly become one of the dominant factors in determining the nature of the world. Of course, we cannot expect to completely understand the world ahead by viewing it solely from a technological point of view. Yet, in this lecture, I shall be doing just that, looking at the future from the admittedly narrow viewpoint of a technologist. This is useful to us, I submit, only if we agree at the outset that there is much more to it, and that the ultimately needed projection is one that will include the sociological factors as well. And look ahead we must. Because despite the fact that much of what will happen is fixed and, in a sense, beyond our control, there still remains that great fraction that we can do something about. To a considerable extent, we can have a better world in the future if we know what we want, or if we recognize what we might otherwise get. The hydrogen bomb. The H-bomb is the established symbol of the growing disparity between rapid scientific change and the lagging adjustment of society. We need to note only that we have learned how to release quickly such tremendous amounts of energy as to be able to destroy all civilization in a world that has not yet produced an accepted, respected mode of conduct to computers and automation for July, 1961. Preclude the use of force. On the other hand, control of tremendous amounts of energy suggests great benefits for society. We should be able even to influence the Earth's weather and the gross features of its terrain. Of course, aside from the fact that large-scale energy release has peaceful as well as warfare applications, the bomb is not the best example of the impact of technology. It emphasizes the military side of the world's problems, whereas, even if no war danger existed, disorder would still threaten if we should fail to assimilate the technological revolution. Outer space. Outer space is the newest symbol of the influence of science on world affairs. We are preparing now for a period ahead in which we shall eventually become a three-dimensional space civilization, rather than being limited as now to the thin film of air over the surface of the Earth. Today, all of the things we are doing in space, either for military or for peacetime pursuits, are no more than extensions of our surface civilization. We orbit equipment around the Earth to assist us with our tasks of control of the operations of our present civilization. Or, in reaching out to more distant space, we are merely probing to learn the facts about it. But surely no one doubts that this is the beginning of a new chapter in the history of man, which must include, before many more pages are written, the ability of man to colonize in a limited way the moon and the near planets if he chooses. And if we put ourselves into a science fiction frame of mind, he may even succeed in creating artificial, permanent planets in various orbits about the Sun as preferred by their adventurous dwellers. Outer space, as the latest major example of the packed potentials of scientific advance, illustrates not only technological innovation but problems of adjustment in our pattern of high on Earth that come with it. For instance, where in space do national boundaries end? How will the world go about judging the contest for use of the limited radio spectrum, as satellite communication repeaters make possible the wholesale interconnection of wide communications into a single, endless, Earth-wide web? What political bodies and agreements will decide how space technology and meteorology will be applied, not only to predict but ultimately to influence the Earth's weather by using nuclear energy? How can international cooperation, which seems so sensible for proper exploration and exploitation of space, be arranged? Intellectronics, nuclear energy developments and outer space conquest will change our way of life. So also will new chemical and biological discoveries. Large increases in man's life expectancy LLIE can say / Kirby 15. For the 20th century is over. But, meanwhile, there is another area of science and technology already emerging, I submit, as the most influential and important for the next decade or two. It will use the greatest fraction of our technical resources, will be most determining in international competition, peace or war, and will very probably emphasize even more the inequality between technological and social advance. A discussion of this area will thus help us especially well to understand the nature of the coming technological society. The rest of this century will see the gross extending of the human intellect and senses by application of science and technology. In every intellectual pursuit in which man is engaged, be it in the professions, in production, in military command, in teaching every where. When we analyze what we do with our minds, we find a part that is best assigned to electronic machines. Reduce the intellectual activity to stored and incoming information, to logical processes, sorting, deciding, and the part that is well understood, that involves rates and quantities too large for the human mind, assigned to the machine. This frees the human intellect for the more complex aspects of the intellectual task, above the routine work of the electronic partner. Give human beings the great pyramid to build without machines, and you will have 1,000 slaves pulling a huge stone, an activity at once beneath man's dignity and his remarkable physical dexterities, and yet at the same time quantitatively above him. One man simply cannot produce more than a token part of the energy that is needed. Similarly, give a human being a series of single-digit numbers to add, and he can perhaps do 1 or 2 combinations a second, and within a few seconds he will be so tired or bored that mistakes will be numerous. Just as a fleet of bulldozers, a huge electric motor, or an H-bomb can surpass by millions or billions of times the energy-producing capability of a human system, so electronic devices can outdo by millions or billions of times the capabilities of human beings. FDR. SimPy, repetitive, intellectual processes. The human brain consists of the equivalent of perhaps 10 billion electron tubes or transistors in a cleverly flexible and reliable, interconnected array. The human mental apparatus is 1,000,000 times more brilliant intellectually than any machine that has so far been built or even conceived. Clearly, such a versatile intellectual capacity should not be applied to tasks that do not require it and that are satisfied by a relatively stupid intellectual machine that specializes. Obviously, we are not talking about automation, the replacement of the factory worker. The words automatic control and computer are also inadequate and narrow. We are speaking of a new man-machine partnership in the powerful domain of the intellect. I like the new word, intellectronics, because it says in one word, extending the intellect by electronics. To show how deeply significant are the possibilities of electronics in basically routine intellectual activities, let us take some brief examples. They will be a bit futuristic, but even where I shall use some exaggeration to make a point, a serious underlying basis will always exist. 3. The practice of law. Consider the practice of law, or at least law as it might be practiced if intellectronics is used to the fullest. 2 or 3 decades from now, every practicing attorney might have in his office a means for convenient electronic connection to a huge national central repository of all the laws, rulings, regulations, and procedures, and commentaries upon them, that he needs. He or his assistant will be able to carry the central repository by operating an electronic input device looking a little like a typewriter. Almost immediately, there will be displayed to him on a special viewing screen any information that is available on his particular question. And this display will cover not just the few possibilities that an unaided, though trained, human brain might have produced in a few days of research in a law library. Instead, the intellectronics system will scan, select, and present in a few seconds the equivalent results of dozens of trained Searchers covering many decades of records over the entire nation. You can see that the intellectronics system and we know how to design such systems today will elevate the lawyer's intellect to the more complex intellectual tasks by giving him better tools with which to work. It will speed up a substantial fraction of legal practice. Even on the non-routine, the more intellectual legal questions, the attorney will be able to consult with the equivalent of a host of informed fellow attorneys. His request to the system for similar cases will yield an immediate response from the central repository, together with comments filed by other attorneys on those cases, even as he himself may later add his experience and ideas into the system for future use by all. Legislating. The National Intellectronics Network to serve the legal profession can serve the lawmaking bodies of government as well, not only in the conventional fashion I have just described, but in two additional important ways. First, since any intellectronics system has to be based upon some kind of logical indexing of the information in its memory so that the information can be retrieved, the initial analysis of the input data for indexing purposes can be expected to emphasize any conflicts or omissions that may exist in the laws and regulations. Second, the intellectronics SYS can readily accommodate the mass of data available on the results of enforcement of the existing laws and regulations. Such comprehensive statistical data should disclose where existing laws and regulations are ineffective, and thus be of prime aid to our law-making bodies. The world is becoming ever more complicated, every action interacts with more other actions, so the rules of our society are correspondingly becoming highly detailed and the procedures increasingly lengthy. Something new to cope with this situation, like an intellectronics system, seems imperative, not just desirable. Medical consultation. How many physicians can your doctor consult with? A practical answer will most often be, maybe 2 or 3. The physician in the future technological age, towards which we are in such rapid transition. Please turn to page 18. Computers and Automation for July, 1961. UI. Wet. Rate. To us. And. R. Stress. What. Us see. Comey. News of computers and data processors. Across the editor's desk. Auto prompt, new advance in numerical control factory production. International Business Machines Corp. 590 Madison Avenue, New York 22, NY. A new computer language, designed to broaden the use of numerically controlled machine tools for automated production of complex parts, was demonstrated on June 14 by this company. Called Auto Prompt, Automatic Programming of Machine, OLS, the computer language enables the user to describe the surfaces of the three-dimensional shape to be milled, instead of describing each path the tool must follow to machine the part. The program leaves to a computer the task of automatically generating the required tool paths on the basis of a simple description, in English-like terms, of the part to be milled and the tool to be used. A flying crane helicopter's large gearbox cover with 20 shaped depressions B. Figure 1 at the right is the helicopter gearbox part, a large round slab of aluminum, with some of its depressions already machined. At the left is the operator's console, Not shown in this picture is the punched paper tape reader, which controls the tool paths. Computers and Automation for July, 1961 IB. Tween ribs was machined in the demonstration. Using a Pratt & Whitney numeric Keller, a tape-controlled continuous path milling machine, and a ball-pointed drill. Deduced from a blueprint, 181 line. Statements in the auto prompt language were written to describe the part completely. Then a solid-state IBM 7090 computer using this information and controlled by the auto prompt master program generated more than 8,000 tool path instructions. They provided the numeric Keller with every tool motion required to machine one of the 20 depressions. Set equals ./1204.9. The computer's instructions, converted to perforated tape for use by the machine tool, enabled the milling job to be completed in about 1/4 the machining time previously required to mill the same part with conventional methods. The saving in lead time is even greater. To produce this part by conventional methods required 3 months from blueprint to production. With auto prompt, any part of similar complexity can be put into production in 2 weeks, 1/6 the lead time normally required. Whole equals cone in /apooo.iapool.ispi 14.625056b4604.971, $2b. Surf T7.952L6655540L.051. Base equals plane plus z/normio.ol.idst2.31. Start equals .lgx/int of I whole tube 2 sidle. Tube 2 equals sil in /axis ptiooo.iap/ooi.irati 12.211. Side 2 equals plane plus y/norm i.309017.95105650.idst.501. Tubl sil out/apooo.iapool.irati 7.721. Side L equals plane y/surfgeo, .50o.ispil, .50o.ispil, .50, 1.1. Remy Sikorsky Region 3. From /sect. Region /seki whole base I. XATI start Y direct, right. Start bound I holiatube 21. CBI holizide 21 bases I 2, tube, sidle, holeisidl. Zigzag. Go to /sect. Stop. Reft. Tube 1. Figure 2 at lower left is a drawing of one of the depressions in the gear box cover. At lower right is a plan of the depression showing the names as signed to the surfaces. At upper left is a selection of the auto prompt program showing the way in which the IBM 7090 computer is instructed in a relatively simple language so that it will produce the tool path specifications. To control the machine tool. Computers and Automation for July, 1961. ABL. POS. STU. TIA. DEAD. AR. ITY. The. We. And. AM. MED. TUR. ORN. The. B. Cal. The. Li. Ins. Vel. Con. FOI. Hun. Me. Art. De1. Tick. In. USC. API. The. BUJ. THL. Tel. A1. Co. TH. E. Al. In. LS. E. ER. A. R. ICS. REN. LONS. RI. LE. The. ISIO. S. SK. EPT. E. E. J61. New Airline Data Processing System. To handle 180,000 reservations per day. The Teleregister Corp., Stamford, Con. United Airlines, Denver, Colorado. North American Phillips Co., New York, NY. The largest integrated electronic data processing system in the business world was officially put into service on June 2 by United Airlines. The system, which has been named Insta-Matic, provides one of the fastest and most accurate reservation service so far developed. 3,000 United Airlines sales agents in 100 locations from coast to coast can make reservations under conditions in which 80% will be handled in less than 1 second. Formerly it required up to 45 minutes for each transaction. The system was produced by the Teleregister Corporation. In size, it is exceeded only by the United States government's early warning defense system. The first phase, system-wide space availability information, went into effect June 2. The second phase, which will provide for space inventory records, flight information, and other capabilities, is to become operational in September. Eventually the system will handle reservations at the rate of 180,000 per day. It took 33 months to build and install and cost approximately $16 million. The equipment includes 3 solid-state electronic data processors, 827 countertop sales agent sets, and 150 tons of communications equipment. This equipment is linked by 12,000 miles of communication circuits. The 3 data processors, telefiles, are located at United Airlines' new $700,000 Reservations Control Center in Denver, Colorado. Information on the availability of seats on each United flight up to 1 year in advance can be stored by the telefiles on magnetic drums. The central processors will be capable of instantly relaying information to sales agents regarding the on-time status of flights, whether a flight is on time or late, and if late, how many minutes and the reason for the delay. They also will be capable of automatically keeping records on magnetic tape of all transactions and producing reports for evaluation of traffic. Such questions as when to add extra sections, computers and automation for July 1961 to flights, or when to reschedule flights as required by traffic demands will receive immediate answers. The high-speed communications units are located at reservation centers in 15 major cities interspersed on the 12,000-mile network. This equipment, supplied for Teleregister by North American Phillips Co., Inc., automatically routes the reservations data to and from the telefiles at Denver and the sales agent sets. The data travels at a rate equivalent to 1,300 words per minute via high-speed American Tel and Tel telephone lines. Intricate communication devices included in the network automatically check errors, determine message destinations, locate operating irregularities, and reroute traffic in case of line failures. The system is interconnected by 12,000 miles of leased circuits. The new transmission and switching SYS TEM is one of the most advanced of its kind in existence and provides a very high degree of reliability. Approximately 500,000 transist ors, 40,000 printed circuits, and 2 million ferrite cores were used. To assure maximum accuracy, the entire high-speed communication system checks itself regularly every second. Should a fault occur in any one of the circuits, it is quite probable no agent would be aware of the situation, because rerouting to functioning lines is extremely fast. Major equipment is duplicated. The standby principle of operation provides instant changeover. Alarm devices indicate the exact location of the trouble. The design eliminates a great proportion of flight booking errors made up till now. This permits greater seat occupancy at all times. Inquiries from passenger stations on the main loops receive answers via the Norelco units in an average time of 1 second. On tributary lines which are tapped to the loops at certain points, the process takes 5 seconds. The high-speed data transmission and switching stations are called concentrators. Each passenger booking location has a push button desk set that is connected to a concentrator only during the momentary period required for inquiry and reply. Each concentrator can serve up to 150 such agent sets. The system is capable of further expansion to handle the requirements imposed. When United Airlines absorbs Capital Airlines, the system can detect errors in messages that are being transmitted. In such cases, 3b. The equipment sends back an error reply to the agent set from which the inquiry originated, or it can send back a repeat request depending on the type of message. The double check provides a highly effective method for detecting all types of transmission errors. Concentrators also operate in seconds to cut out a faulty section of line in a loop, rerouting the traffic via the good section of line on each side of the fault. When trouble is eliminated, the concentrators immediately close the loop and return to the normal operating arrangement. The new system can accommodate many types of transmission codes, including 5-level teletype, 6-bit computer code, and those commonly employed for punched card operations. Speed of transmission depends on the codes used, message length, and other factors. Line loading on the new United Airlines flight reservation system will probably not exceed 60%, and the time needed to get a response to an inquiry at concentrator locations will average 1 second or less. Tragic waste due to Model T management of information on current federal research indicated. United States Senate Committee on Government Operations, Subcommittee on Reorganization and International Organizations, Washington 25, D.C. The federal government's Model T methods of managing scientific information contribute to unknowing duplication and tragic and intolerable waste of men, money, and matter. Senator Hubert H. Humphrey, D., Minnesota, declared in April. He urged federal agencies to master the scientific revolution in information control. He made the recommendation in personal conclusions to a 278-page report, issued by a Senate Government Operations Subcommittee of which he is chairman. Efficiency in $8.1 billion in spending involved. The report states that there are no indexed interagency inventory of an estimated 160,000 projects involved in $8.1 billion of current federally financed research and development projects. Various agency information systems are designed to cover at least Part 6 FT effort. B. JT. The systems are a hodgepodge over lapping, underplanned, under no URI shed and underused, Humphrey states. 4b. For the federal government to rely on present methods, he said, is no way to run a railroad or a race for survival. Information control key to man in space. No administrator or scientist, however competent, can attempt to know personally about all current work in progress which is related to his field, the report states. Yet, Senator Humphrey observes, knowledge of work in progress is a key to effectiveness in many fields, to man in space, to control of the weather, probing the ocean depths, drilling into the Earth's crust, bombarding the nucleus of the atom, deciphering the code of life, or unlocking the secrets of why plants are green. The National Aeronautics and Space Administration has no central index of all its in-house and extramural research and development projects, now in process, the report observes. Science Information Exchange. It adds that partly because of the Senate committee's urging, several federal agencies, including NASA and the Defense Department, have organized a science information exchange for the registration of all current research projects. However, the exchange has hardly begun operations in the physical, social, engineering and mathematical sciences. Previously, the exchange has registered 30,000 current projects in the biological and medical sciences. But, the report states, agencies have not used even the medical coverage to its fullest potentiality. The report criticizes lost effort and unknowing duplication in federal research and development. Sufficient attention has not yet been given to the problem of salvaging results from vast investment in contracts and subcontracts which are cancelled prior to producing finished hardware. More than $2 billion of such contracts and subcontracts were cancelled in the last 3 fiscal years. Another of the important phases of the information problem concerns duplication of effort either on an intentional or unintentional basis. The Department of Defense does not have a reliable study on the extent of unintentional duplication, but some estimates run as high as 10%. New procedures to salvage information from cancelled contracts and to prevent unknowing duplication were urged by Humphrey in letters to the new administration, shortly after the January 1961 changeover. At that time, the Committee on Government Operations approved the key points in the subcommittee's report. Computers and Automation for July, 1961. WIT. pH. 10. TYI. ST. LOC. COL. In. 19A. TH. COR. So. Per. Pal. ECL. In. Of. PJ. Hi. FRE. I'm. Po. Vel. 12. FOL. CH. 2. RA1. D. Del. CH. AR. OV Euro. Ad. Mal. ABJ. ST. TI. Ad. CH Euro. 31. HAL. 10. Com. TND. I. At. The. There. LE in. And. LRD. 11. 11. A. ET. D. P. Shin. Anged. Ed. Unter. At. 1. Ons. S. D. Rs. With. E of. 61. Solid-state tunnel triode. Bendix Corporation. Research Laboratories DIV. Northwestern and L Mile Road. Southfield, Detroit, Mich. Introduced for the first time in May, at the Bendix Research Laboratories Divisions. Symposium on Information Processing and Computer Technology was a new solid-state tunnel device by Dr. H. F. Mattert, Research Laboratories Scientist. The new tunnel triode represents a major step forward in the use of high-speed tunnel diode techniques, which have permitted computer memories to achieve extremely high speeds. In the earlier use of tunnel diodes as memory elements, the act of retrieving the information stored in the diode caused the memory state to be erased, whenever the computer sought to determine the stored information. This required the reconditioning of the diode each time in order to restore it to its original memory state. The new tunnel triode technique permits non-destructive readout, because the third terminal can be used to sense the binary state condition of the triode without affecting its memory content. The triode described by Dr. Matteret makes use of certain properties of unipolar transistors invented and developed by him several years ago. This tunnel triode, or unipolar tunnel transistor, appears to constitute a marked improvement over previous devices which attempted to sense the state of the tunnel diode. Previous methods were limited in speed, which is the main advantage of the tunnel diode, because of two effects known as carrier storage and relaxation. The unipolar tunnel transistor will be relatively insensitive to these effects and will, therefore, retain the high-speed advantage of the tunnel devices. Mobile computer demonstrations for executives. Royal McBee Corporation. Port Chester, NY. 3 Royal McBee officials were on hand at the end of April for the dispatching of the first of 4 mobile, 50-foot-long computer AMAs, which are now beginning a 100,000-mile-a-year tour of American cities. The market for electronic computing equipment now reaches computers and automation for July 1961 to companies of all sizes, and selling in. This market requires the adoption of a highly flexible technique for marketing by adequate demonstration. The complex data processing equipment, even if small scale. The compute ARAMAs will provide demonstrations to executives of electronic computing and data processing equipment. 2 Royal Precision computers and data processors, 1 LGP30 and 1 RPC4000, are housed in each trailer. They will be taken literally to the door steps of businesses, research and scientific organizations, government agencies, and universities throughout the United States. About 500 Royal Precision Computer installations have been made to date. Free data processing training courses. Philco Corporation. Computer Division. Willow Grove, PA. A 3-day seminar, design specific. Ally as an introductory course to data processing, has been scheduled for July 5, 6, and 7 by this division. The sessions will be held from 8:30 a.m. to 10:30 a.m. Eastern Daylight Time in the computer divisions. Facility at 3900 Welsh Road, Willow Grove. The course is primarily designed for operating, supervisory and secretarial personnel to acquaint them with the basic elements of data processing. There is no charge for the seminar. Enrollment can be made by writing to C.A. Leventhal, Manager of Customer Education, Philco Computer Division. 5b. Merging of Plant and Office Automation. George M. Mushamp, Vice President, Industrial Products Group. Minneapolis Honeywell Regulator Co. Minneapolis, Min. Based on a paper given at the 5th Conference on Manufacturing Automation, Purdue University. Lafayette, IND, April 17, 1961. A new era in industrial automation, in which automatic controls in the plant will be married to data processing equipment in the office, is in the offing for U.S. industry. The successful consummation of this marriage could constitute the greatest industrial event of the 1960s. The effects of this marriage will be to produce more goods more economically, to provide more of the types of jobs that can be done better by people, and to require more education to fit people for these jobs. The issue may prove to be the most important confronting every major industrial enterprise. For management, it will mean more work, if we are to bring this wedding off as an economical union and not as a costly collision. Automatic operations in plants and offices already have attained a high degree of development. It is possible now to merge these two massive developments. We can reorganize the paperwork, the present end product of most automatic office equipment, so that the information, in addition to serving as a record, can be fed automatically into plant control systems. We can automatically acquire from the process both the information needed for automatic control and the information needed for accounting. We can automatically feed the necessary information back to the process for automatic control. This will lead to parallel automatic operations in place of the present man-machine serial operations. It is becoming more and more difficult to draw a clean line of separation between automatic control in the plant and automatic data processing equipment in the office. The immense challenge before management is to minimize the intolerable and costly overlapping which will occur if we continue the separate pursuit of plant and office automation. 6b. While automatic operations for a whole enterprise can become complex, they can be built step by step. An example is provided by one of the nation's largest electric companies, Philadelphia Electric. The company is installing an online digital computer whose primary function will be to direct the network control system to Make certain that power is always produced at minimum cost. But the computer also will perform a secondary function by obtaining basic data for billing of power exchanged between interconnected companies. Meeting on Computer Storage Allocation. A.W. Holt, Chairman, Storage Allocation Committee, Association for Computing Machinery. C/O Applied Data Research Incorporated. 759 State Road, Princeton, NJ. The Storage Allocation Committee of the Association for Computing Machinery held an open technical meeting in Princeton, NJ, on June 23 and 24, 1961, under the sponsorship of Applied Data Research Incorporated. The purpose of the committee is to facilitate and encourage the exchange of information and to stimulate new work on the subject. The storage allocation problem is the problem of finding computational methods for carrying out part or all of the assignment, use, and control of all forms of information retention available in the environment of a computing system. At the Princeton meeting, technical papers were presented on automatic storage allocation techniques and their applications to real-time systems. Discussion on the subjects toward a definition of the storage allocation problem, and pre-planned vs. dynamic methods of storage allocation, were held. Computers and Automation for July, 1961. Section, in 1. DRJ. THJ. NE. NI. at J. Rad. Ma. And. In 1. Phil. INF. Cal. Of. REQ. Cat. Phi. Of. H. Fro. Con. Cal. A 1. $10. Cap. Pre. Com. Ons. C. Nman. RN. CI. N. ACH. GY. Rs. Edic. E. S. C. E. Lit. RLCY. RL. IS. LS. No. Backslash. Micro Miniature Computer Unit, Parallel Adder. General Electric Co. Receiving Tube Department. OFTURA, KY. A micro miniature computer unit about the size of a package of cigarettes was demonstrated in March by this company. The tiny computer showed the feasibility of using General Electric's TIM, thermionic integrated micro module, concept for data processing systems. The developmental model displayed was a 3-bit parallel adder containing 16 NOR modules. The TIM components themselves, arranged in stacks of 4, are about the size of 4 cigarettes. The TIM components are radiation tolerant, and they withstand both pulse and steady state radiation with little or no effects during or after exposure. Also, TIM circuits need very little power, only 240 milliwatts. In the case of the 98-tube display computer, the TIM concept is especially useful for applications requiring high component density equipment where radiation is encountered. These include computers used for GUID and SIN missile for nuclear reactor controls, and for satellite applications. Designed to operate at 580 degrees C. TIM circuits make use of the heat that would normally cause malfunction in transistorized computers. Each of the 16 modules in the demonstration computer contained a triode, 5 diodes, and 2 resistors. Thus, the 3-bit PAR adder contained 130 components. Although the demonstration unit was not packaged in optimum form, its component density is about 43,000 per cubic foot. Concede. Arably higher component density is possible. The entire unit could be built into a space of 1.8 cubic inches, which would represent an operating density of 125,000 per cubic foot. This estimate is based on a predicted packing factor of 30 per int, including leads. Weight of the 130 components, plus spacers, was only 1.38 ounces. Computers and Automation for July, 1961. Commercial Data Processing Service. Established by a bank. The Waterbury National Bank. Waterbury, Con. And Bendix Corporation. Bendix Computer Division. 5630 Arborvitae Street, Los Angeles 45, California. The Waterbury National Bank announced in March that it has signed an agreement with the Bendix Corporation for lease of data processing equipment manufactured by the company's computer division. The bank is beginning a data processing project unique to banking in the United States, and is believed to be the first national bank to establish a commercial data processing service. This pilot plan operation has been authorized by supervisory authorities. Experience gained in this project may be used as a guide for the 13,000 commercial banks in this country to facilitate development of the service. Bureau, the Automated Accounting Center of Connecticut, was organized as a division of the Waterbury National Bank. This division will furnish data processing services to companies, which, like the bank, cannot afford to set up an installation exclusively for their own use. The center's service will be sold on a time and fee basis to any business in the state, and in certain areas in bordering states. The bank will not furnish the services free in exchange for deposit accounts or increases in deposit balances. The service will be priced to be profitable to the bank, as well as economical to even small business firms. To familiarize businessmen with the center's operation, a series of special data processing seminars will be conducted by the bank. These sessions will serve to introduce the new technology to many organizations which do not have computing machinery. The bank is hopeful that the project will stimulate the economic growth of the community and the state. The data processing system is in the medium price range, $50,000 to $500,000, and will be linked into a magnetic ink sorter reader. In addition to processing information from punched paper tape and magnetic tape, the computer will process data read directly from magnetic ink symbols and numbers pre-printed, or checks, deposit slips, and any other paper of workable size and weight. 78. When all components of the system are fully integrated, 2/3 of the computing center's time will be used to process large quantities of business and industrial data. The remaining time will be utilized by the bank for its accounting work. It is expected that the automated accounting ing Center of Connecticut will serve the following types of businesses: manufacturing, concerns of all types and sizes, paper, brass, and textile mills, wholesale supply houses, industrial, building, food, drug, etc., accountants, supermarkets, department and clothing stores, publishers, engineering firms, all businesses with delivery routes, utilities, insurance agencies, hospitals, banks, and many others. 1,000 controllable switches in less than cubic foot. Taurus Corporation, Lambertville, NJ. A new punched card switch has been developed by this company. The model KI000 punched card switch provides 1,000 switches operable from a card supplied by the company having 20 rows by 50 columns. There is a separate switch for each hole position. After 8B, the card is inserted and the operating lever is pushed, the punched holes have closed switches and the unpunched holes have open switches. The unit thus lends itself to automatic control of machinery, for example, where patchboard programming has been found insufficient. Many previous units of this type made by this company have been cycled over 100,000 times without failure. Units used constantly for over 4 years are still giving reliable and trouble-free service. This reliability is attributed to gold plating used over silver plating in the switch contacts. Computers and Automation for July, 1961. F. I. Uni. B. AIM. H. ADV. Ver. N. IC. Mac. INF. ELE. POC. and INF. In. BOC. MO. CN. ES1. M. HA. 8. I. 2. RNA. WOI. PU. FA. Of. AC. In. Co. CC. Ver. N. Auto. Where. LSUV. EBY. O. NTLY. Able. TI. IL. 961. H. F. T. I. Application of automation to libraries. To be studied. Werner W. Clapp, President. Council on Library Resources Incorporated. 1025 Connecticut Avenue NW. Washington 6, D.C. A $50,000 grant to the Library of the University of Illinois Chicago Division has been made by this council, for a project aimed at helping university libraries in the age of automation. The purpose of the project is to apply advanced data processing techniques to university library procedures, and to develop an overall system using the latest electron IC equipment, as well as to adapt business machines for library use. The research staff will work with the Information Systems Division of the General Electric Co. on the project. Many library procedures have not kept pace with the increasing number of patrons and the tremendous increase in the amount of information now available. The number of titles published annually in the US has increased 46% since 1929. Books classified as technical, which are those most used in university libraries, have increased 94% in the same time. In the field of periodicals alone, it is estimated that more than 50,000 are published annually in 60 different languages. The unprecedented growth in libraries has not been matched by the output of graduate 8 library schools. The subjects of the study include 1. Mechanization of cataloging procedures. 2. Determination of the advisability of automatic compilation of a book catalog which would have general distribution on the campus. 3. Dissemination of information to faculty and research staff. 4. Microstage of library materials. 5. An investigation of acquisition and circulation procedures. 11. AUTOL/JOTIC document sorting and accounting using plastic jackets. International Telephone and Telegraph Corp. ITT 67, Broad Street, New York 4, NY. An automatic document sorting and AC counting system for department stores and computers and automation for July, 1961. Similar large retail establishments was described by this company at a recent convention of the National Retail Merchants Association. This system is based on the jacket concept, which uses a transparent plastic jacket to carry the original document or sales slip through the entire process. All the information required for processing is coded on a strip of magnetic tape fastened to the jacket. Once an operator codes information on the strip, the document is automatically inserted into the jacket and all subsequent operations are completed without manual processing. The next operation is to sequence the jacket by account number in the classifier, which merges at a speed of 10 per second and sequence up to 3 or 4 per second. Again cognizing the information recorded on the strlp of magnetic tape, the jacket reader transfers the data to a computer at a speed of 5 items a second. The data processor, 1, calculates cyclic and control totals and various taxes. 2, updates the accounts receivable file. 3, produces aged account receivable reports. 4, prints customer statements. 5, processes changes to the accounts receivable file, and 6, produces management reports. It can also be used for payroll, accounts payable and inventory control. When the information on the jacket has been fully processed, the document is automatically removed from its plastic protective envelope and stacked sequentially for later inclusion in the customer's statement. Intelex points out that the new system requires no new sales floor procedures, retains country club billing methods, retains the present paper sales check, and provides the current credit status of individual accounts. Another advantage lies in the fact that the original source document travels throughout the original system with its related electronic coding for reference and audit trail purposes. 9b. Digital computers used to predict tile quality of metal castings. Ellis Foster and B. L. Fletcher. Battelle Memorial Institute. Columbus 1, Ohio. Digital computers can now be used to eliminate trial and error experiments in predicting the quality of metal castings. The key to computer analysis of castings is a method of accurately predicting the patterns of heat removal from a solidifying casting. With this established, almost every variable of the casting process can be evaluated on the basis of its effect on solidify, cation and soundness of the ingot. The first step in studying casting problems by computer is to describe the physical situation in terms of a mathematical model, which can be used to predict the thermal behavior over time of a casting under specified conditions. Once the computed predictions have been checked by experimental work, the mathematical model can then be used to predict the effects of altered casting procedures or shapes without further experimentation. Computer analysis is especially valuable for intrinsically expensive cast metals like uranium and for cast metals like niobium and molybdenum, which are easily affected by defects in the castings. This analytical technique could also be applied to continuous casting, where it is inconvenient to vary conditions experiment because of the large-scale operation, to developing specifications for shapes and sizes of risers by evaluating mold materials, pouring temperatures, and metal properties, and to heat treating by evaluating how long and at what temperature metal should be kept in furnaces or baths to achieve a desired result. Fabrication processes also have characteristics that CBN he studied by the techniques. For example, the temperature attained by a forging is the product of the metal properties, the energy imparted in forming the metal's initial temperature, and the heat losses by conduction, convection, and radiation. The mechanical properties also vary with temperature, and the ability of a material to be formed may lie within a certain temperature range. Lob. Investment firm uses computer to project stock earnings. Radio Corporation of America, New York, NY. An electronic computer is at work forming the detailed statistical calculations of investment analysis for the Lehman Corp. in cooperation with the RCA Electronic Systems Center at 45 Wall Street, NY. Lehman Corp is projecting future common stock earnings for some 200 public utility companies. The earnings projection is one of the principal factors, among many others, used by management in making investment decisions. The investment company provides the center with 20 coded punch cards for each utility, containing 175 items such as energy, unit sales, rate base, capital structure, rates of return, and cash flow, among others. This information is converted to magnetic tape and introduced into the computer. The computer projects the common stock earnings for each company for the next 4 years AC, according to a formula. To achieve the same results by conventional means would require a total of approximately 400 man-days. Earnings projections of the various companies need be calculated simultaneously to be meaningful. So 8 new factor of efficiency has been introduced in the decision-making process affecting this important area of investment. In projecting the COMOB stock earnings, both a rate-based method and a unit yields method is used. Once the analytical work is programmed, it will be possible to feed up dated information into the data processing system at any future time and print out the desired results in minutes. Computers and Automation for July, 1961. MICR. Size. Stra. Of U. INTE. SES. THRE. Mod L. Air C. Size. Ant. STA1. Doer J. Nay. In 1. 4. Den L. Eric. Ankle. And. TIML. Wow. Tor. Tio. And. All. POC. ITY. Era. The. Of. Op. T. Lack. Way. Was. Com. IE. E. Ed. OM. Ill. O. D. Ill. The. N. On. IP. SE. O. I of. G. ND. Ishan. NG. IE. ONS. Sub. Re. Air. 961. Microfilm search at 100 pages a second. FMA Incorporated. 142 Nevada Street. El Segundo, California. A new machine which can automatically search a 32,000 page file and present desired information in less time than it takes to drink a cup of coffee has been developed by this company. Called File Search, the machine combines new advances in optical and electronic techniques, and is able to retrieve stored information from microfilmed files at the fastest rate yet known. The system stores 32,000 standard-sized magazine pages on a single reel of microfilm, and can accommodate over 1,600,000 pages of information, enough to crowd 44-drawer file cabinets, in a single file cabinet. When information is desired, the machine automatically searches the microfilm reels at the rate of 100 pages a second, making copies of the requested material. With this machine, a researcher can locate in a few minutes all the data on a specific FIC subject from an accumulation of thousands of pages of reports or documents. In an average working day he can obtain selected data from over 3 million pages on file. The machine has been designed to meet the commercial need for an economical and practical system of information storage and retrieval. The price of the system, slightly over $100,000, is far below that of any other system capable of automatically performing such comprehensive information storage and retrieval. Computers and Automation for July, 1961. This company has established production schedules for the machine. The first system has been sold to the Navy's Bureau of Ships, Washington, D.C., with delivery scheduled within the next month. The system is basically composed of a recording unit and a retrieval unit. The recording unit photographs files of documents, along with a description of each document's contents, which is coded in the form of opaque spots. These are stored together on reels of microfilm. The machine, from its request card input to its printed hard copy or film output, is integrated into a single console, 71x55x50 inches, except for a recording camera and simple indexing machine. No associated units, such as computers, card readers, etc., are required. The retrieval unit searches for and finds the facts desired. It can check 6,400 standard pages, XLL, on film per minute. and select out for viewing or printing, hard copy or film, any of those pages containing the type of information requested. Requests for information originally are fed into the machine by punched cards. The system can handle up to 6 requests simultaneously. And facts requested from the masses of information stored on film may be projected on the machine screen for viewing by the requester. If permanent, usable records on paper are required, the machine then produces an immediate hard copy print of the document. 120 businessmen play mass management game. Radio Corporation of America. 30, Rockefeller Plaza, New York. 20, NY. If an electronic computer can evaluate all the variables of a national election and accurately forecast the winner, then it should be able to predict sales trends for a business operating on that premise. 120 Midwest executives divided into 26-man teams competed with each other at the RCA Electronic Data Processing Center in Chicago on March 18. 3. Management game, to demonstrate their ability to manage a business with the aid of modern forecasting methods. The game was staged for the 8th annual Midwest Confer INS. The game, designed especially for the conference by RCA, used the techniques DevSecOps in RCA's successful forecasting of the Lib. 1960 presidential election. It dealt with management problems such as sales forecast, inventory management, and profit optimization. All the competing teams were assigned to operate the same imaginary company over a period of 3 years with the goal of turning it into the most profitable concern in the industry. The company executives were required to base inventories on their sales needs during the 3-month period beyond the date of the forecasts. Forecasting techniques similar to those used by CA in predicting the Kennedy victory were employed to provide market data to the management teams. Armed with this information, each team made its own decisions regarding future inventories, the primary factor in measuring profit or loss. 7 factors that might influence the imaginary company's sales were fed into the 501 computer, along with management's decisions. They were current bank interest rates, federal spending, employment level, consumer spending on certain luxury items, income lost due to strikes, average farm spending, retail automobile sales. Programming had been done in advance. The computer required only 40 seconds to provide each sales forecast. Programming of a sales forecasting method similar to the one used in the game for the average company requires 6 man-months of work, but once it is done, it is permanent. In contrast, a man working with a desk computer would require 3 months to arrive at the information needed for each forecast. And virtually all of his work would have to be repeated for each period of operation. In the game played Saturday, 30 minutes were allowed for each management operation, covering 1/4 of a year. The entire game lasted from 9 a.m. to 4 p.m., with an hour's break for lunch. It was the final event of the conference, which was co-sponsored by the Chicago chapter of the American Statistical Association and the Chicago Association of Commerce and Industry. 12b. How fingertip counters Keep ahead of hat sales. Vita Root Inc. 70 Sargent Street, Hartford 2, Con. Fingertip counters have saved time and money by replacing laborious book and card systems for recording sales of boys' hats at the Peckett Headwear Company, New York. This 50-year-old firm was faced with the problem of keeping tabs on orders for some 300 different styles of hats, with the further complication of having each style available in 5 or 6 colors. At first, a card system was devised, and this was then discarded in favor of standard books. Both of these methods, however, involved thumbing monotonously through lists, papers, and pages before a single notation could be made, causing both delays and exceptional inaccuracies. Finally, Sam Strauss, office manager, decided to try banks of multiple unit reset counters, known as the Very Tally system. These are mechanical, 4-digit counting devices which advance 1 unit at fingertip pressure on a front lever. Peckett's present Very Tally installation consists of 1,152 individual counters, arranged in banks, see photo. There are 12 banks, each consisting of individual units mounted 6 tiers high and 16 wide. Each counter is marked with the style and color of a hat, such as red 357, royal 1386, charcoal 237, willow 449, etc. These designations are changed approximately every 9 months. When a new line is introduced, when a purchase order has been filled, a secretary goes to the Very Tally counters and presses off the sale in accordance with the order. Each digit represents the sale of 1/2 dozen hats. Computers and Automation for July, 1961. The Sim. Put. Tull. Lab. Magel. Tui. Corn. SPE. MEM. INF. MEM. Put. Tia. The. It's. No. Ter. STA. Ing. Use. Ist. Yet. Tull. March, ATT. Ode. WH. Die. STE. TRC. The. High. Mole. At. Phil. M. A dash. FO. Com. N. NA. E. ER. Is. Yet. Nork. Nonnating. The. Og. Cleus. Or. Reen. Imin. In. P. Lnate. .es. Have. Or. Y. N. I. Cur. L. S. ND. And. N. On. NG. F. Led. E. N. N. E. Able. A. In. Ones. S. 61. Bank goes to EDP for deposit, installment, loan, corporate trust, and personal trust accounting. Pittsburgh National Bank. P.O. Box 777. Pittsburgh 30, PA. Contracts have been signed by this bank with the General Electric Company for 2 PLA GE225 all transistorized computer SYS. TEMS. The new equipment, the first of its type to be installed in the eastern United States, will be used for deposit, installment, loan, corporate trust, and personal trust AC. Counting. The first of the electronic data processing systems will be installed in the summer of 1962. The second system will be installed by the end of that year. The total system will consist of 2 GE225 computers, 4 document sorter readers, 10 magnetic tape units, a punched card reader and a punched paper reader, and 3 high-speed printers. One of the GE225 computers will be equipped with a magnetic tape system for storing and maintaining the account files for each of the applications. The second computer will perform all the data conversion operations. High-speed printers will convert information from the computers to printed form. For customers checking accounts, for instance, magnetically encoded checks and deposit tickets will be read by the data conversion computer at an effective rate of 120,000 documents per hour. A battery of 4 document sorters will then arrange the checks in proper order for giving information to the computer, each fine sorting at the rate of 14,000 checks an hour. The file processing computer will then digest the information. For the bank's demand deposit accounts, the computer will calculate changes and post accounts at the rate of 1,500 a minute. To post checks, deposits, rejects, overdrafts, stop payments, watch for holds, and perform other steps, the computer will make 16,000 calculations a second. Finally, each high-speed printer will be able to turn out 1,500 complete customer statements per hour. When the first system goes into operation, it will be used to process all checks and deposits for the bank's 60,000 deluxe checking accounts, which represent about 30,000 items a day. In addition, it will handle the transactions for approximately 105,000 time plan consumer loan accounts. Computers and automation for July 1961. Upon completion of the second installation, the combined system will handle all deposit and check processing for the bank's 170,000 checking accounts, representing a total volume of approximately 190,000 items per day. Corporate trust, personal trust, and transit operations will then be converted to the new electronic data processing system. The system was designed by the bank's Automation Development Division and a team of specialists on computer systems from the management consulting firm of Booz, Allen and Hamilton. Reading and writing on magnetic tape at 1,200 bits per inch. Potter Instrument Co. Sunnyside Boulevard, Plainview, NY. A new standard high-density, high-precision tape handler system has been developed by this company. The unit is named the PhD 1200 high-density system and includes the 90,611 high-density tape handler used in the Bendix G20 system. This high-density magnetic digital tape recording system offers the ability to read and write tapes at packing densities of 1,200 bits per inch with extreme reliability. Transient error rates are fewer than I bit. In 10.8, permanent error rates are less than I bit. In 10.10, more than 20,000 passes of The same tape can be made without losing in formation or increasing the transient dropout rate. Dropouts are fewer than I in 10 billion. At 1,200 bits per inch. More than 20,000 passes of the tape can be made without losing information or significantly increasing the reading error rate. The tape transport operates at a tape speed of 100 inches per second with a packing density of 1,200 bits per inch, and a rewind speed of 200 inches per second. The 1-inch wide tape contains 8 information channels, 1 block marker channel, and 1 parity channel. 13b. Model of computer-controlled TV station of the future shown. Radio Corporation of America. 30, Rockefeller Plaza, New York 20, NY. A fully automated television station, with both broadcast programming and station business procedures under complete control of a computer system, has been developed for the broadcasting industry. It was exhibited in May BRCA at the meeting of the National Association of Broadcasters in Washington, D.C. This equipment makes possible television stations entirely controlled by an integrated electronic system. C.H. College, Division Vice President and General Manager, RCA Broadcast and Television Equipment Division, said the RCA concept represented the ultimate in television station automation, a goal toward which the industry is moving rapidly. A business as complex as a television station, with its technical side, its sales, operation, billing, news, traffic, and many other aspects, can realize substantial efficiencies from automated control. And Mr. College said, "We visualize the broadcaster approaching full automation not all at once but in a 3-step process. First, modernization of his technical equipment, next, simplification of operational controls, and finally, the integration of all station operations." With the television industry's rapid growth, function upon function has been added to station broadcast operations, greatly complicating the control problem and creating a confusing array of buttons to push and knobs to turn. Equipment improvements have been introduced to speed the march toward automatic control, with its benefits of greater efficiency and the reduction of the chance of human error. In station modernization programs, the use of such equipment is a first stride toward automation. Some of the most recent improvements in this direction include a continuous loop for film projectors, semi-automatic live cameras, random access tape with automatic cue, and an automatic announcer. The automatic announcer is a combination of RCA's RT7 cartridge tape recorder 14B and its TP7 slide projector, providing a complete sequence of slides synchronized with a recorded announcement. The unit may be operated by push button or by a signal cue from other equipment. Total automation ENV1S1 owns the complete integration of the broadcasting and technical functions with those of the business office, using electronic data processing both for on-the-air switching and for such activities as time availabilities, adjacencies, schedules, and billing, among others. Third International Congress on Cybernetics. Namur, Belgium, Sept 11-15, 1961. Secretariat. Association Internationale de Cyberneurotique. 13, Rue Bas Marcel. Namur, Belgium. The Third International Congress on Cybernetics, called by the International Association for Cybernetics, will be held at Namur, Belgium, September 11 to 15, 1961. 5 main themes will be considered. 1. The bases and methods of cybernetics. 2. Semantic machines. 3. Automation, technical aspects. 4. Automation, economic and social aspects. 5. Cybernetics and life. A general opening lecture will be given by Mr. Georges Villers, President of the French National Employers Council. General lectures followed by discussions will be given also as follows. Cybernetics and Biology by Dr. Henry Laborit, Principal Physician of the French National Navy, Director of the Ethnological Laboratory of the Physio-Biological Research Section, Paris. September 12. Cybernetics of Evolution and Self-Organization by Mr. Gordon A. Pask. System Research Limited, Richmond, Sept. 13. Variability and Specificity by Mr. Fran Ois Bonsack, Professor at the Federal Polytechnic High School, Zurich, Switzerland, September 14. For further information, please write to the Secretariat. Computers and Automation for July, 1961. Th. Nor. PROC. OFFI. Unit. Matty. ACU. 3000. Sheol. Sheol 1. Wool. Forn. Each. Ist-E. ONL. 1. ABIJ. The. Inv. Authl. In. VAT. Tool. App. ELE. Sal. Tia. 12. R. Res. C. In. Mag. Of. H. Fu. Law 1. RET. Cal. Ma. Do. Sui. Com. Ed. Ided. E. Th. Ter. Ods. Iro. Liler. 2. 961. Determination of weather variables. Using new devices and a computer. Armor Research Foundation. Illinois Institute of Technology. 35 West 33rd Street. Chicago 16, Ill. Accurate determination of weather variables in areas up to 25 miles away is now possible without venturing into the area under study, according to scientists at this foundation. A study indicates that it is possible to determine the following weather variables at a remote point: temperature A, relative humidity Yj, air pressure A, wind direction J, wind speed. The proposed system also can determine these weather factors at heights up to 5,000 feet. And, using an accompanying computer, provide a meteorological profile. Here is how the system would work. 2. Methods would be used for measuring temperature by passive means. A microwave radiometer to measure the emission from oxygen in the 60 kmc region of the microwave spectrum. J. B. A radiometer to measure the emission from carbon dioxide in the 4.3 micron region of the infrared spectrum. One means is primarily a radar instrument, the other an optical instrument. These radiometer readings would be vert to temperature height profiles, and complement one another, providing fuller information. The technique for measuring relative humidity is similar to the technique for measuring temperature. The main differences are in frequencies of the radiometers. Wind information would be obtained by detecting acoustic disturbances along a vertical line by an array of ground stations. In this method, rocket grenades would be used to produce the acoustic disturbances. Appropriately placed stations would detect the time and angle of arrival of each sound burst. This data, coupled with information of the position of the explosions, atmospheric temperature, relative humidity, and density, allow the wind structure to be deduced. Using knowledge of air pressure at the ground, and the temperature and relative humidity data from the radiometers, the pressure height profile is easily constructed by a computer. Computers and Automation for July, 1961. The digital computer reduces the large quantity of measurement data to condensed answers. The proposed system would help fill the present gap in the measurement of micrometeorological variables. Transistorized desk calculating machine. Electrosolids Corp. 13745, Saticoy Street, Panorama City, California. A fully transistorized solid-state desk calculator with instant response and no moving parts is being developed by this company. Called TAC, Transistorized Automatic Calculator, it is designed to compete in price with conventional mechanical machines. High ER reliability is expected from the fact th.at electrons can transfer information instead of gears and cams. Since electrons travel at the speed of light, the new calculator performs addition, subtraction, multiplication, and division almost instantaneously, while mechanical machines require several seconds to work out some of their functions. The sales in the desk calculator business today is estimated at $60 million to $75,000,000 per year. However, no machines currently marketed are transistorized. The new desk compute ER is expected to enter the market late in 1961. Comparable 10-column calculators cost as high as $695. The new computer is expected to sell for $495. Computron Corp., a subsidiary of Electro Solids, will manufacture the new computers. The subsidiary will be under the direction of Dr. Stanley Frankel, a former consultant of General Electric and Packard Bell. Dr. Frankel has been active in the field of electronic computers since 1947. He formerly taught at California Institute of Technology. 15b. High-speed testing of electronic components by SAT. General Precision Incorporated. Lyroscope Div. Glendale 1, California. A new system for high-speed testing of electronic components has been introduced by this company. The system, called SAT for Semi-Automated IC Test Equipment, is designed to replace tedious manual testing now necessary to check component reliability. The system will evaluate components for combinations of 10 parameters and accept or reject each at a machine rate of 1,800 components per hour. One of the first systems is in use testing transistors, and is providing a saving of 96% over the cost of performing the equivalent manual tests. Each module in the electronic console controls one of 10 test stations in the mechanical handling console, shown in the picture at the right. The modules contain binary type logic circuitry for making go/no go decisions. Each module is provided with controls for setting test conditions and establishing parameter limits. An operator inserts components in a revolving table in the mechanical handling console. The table carries the component to each of the 10 test stations. At each station, the component is tested for a different parameter and is automatically rejected if it fails to meet predetermined limits. Plug-in modular circuitry incorporated in the design of SAT permits flexibility in application for immediate uses and adaptation to changes in the state of the art in the electronic component industry. SAT automatically performs continuing self-checking during operation to ensure testing accuracy. L6B Computers and Automation for July, 1961. Bro. Mad. Com.L. By T. Of. ABL. The. Comp. As it. The. Actic. Con. In. Ions. At he. F the. Nput. Tim. Lial. Eon. Over. Doug. Few. Lick. Few. Janicl. The. Dwe. Vat. Twil. MRK. Pruk. Twil. Lsult. Vat. Cases. Ltril. Rat. Later. Lure. The. S of. Anal. Anal. Item. Seeing. Ma. Lpud. Fa. The. Sys. Veil. Laws. Lotta. Ions. Law. Lore. Lher. 19 Li. EAS. Tulu. Iv. Ilh. LWO. Iral. Ion. 1. IL. You can solve your computer problems quickly and economically by using our 32K word storage IBM 704. Whether you need long or short runs, they can be readily scheduled on our machine at the same attractive rate for every shift. $275 per hour, including all peripheral equipment and operators. Bring your program to us and work in our client's room between runs, or mail us your program with instructions for running it, and we will mail back the printout within 24 hours, or simply leave your entire problem in the hands of our capable mathematical analysts and programmers whose skills can be relied upon. If you need pipe stress, structural stress, flow analysis, or curve fitting, one of our general programs might well be just what you are looking for. To take advantage of our prompt, efficient computer services, write, wire or call us. Collect, Hilltop 5 to 4321, extension 1449. Electric Boat GEES 6 ACSGA. Computers Alt Automation 4. July, 19 GI. Ad infinitum. 17. The Coming Technological Society. Continued from page 16. Will also routinely introduce his data on a patient into a network of consultative wisdom. The patient's entire history, the results of all tests, the symptoms and complaints, and a statement of the family background of inherited tendencies. All this will be efficiently introduced into the medical intellectronics System. The system will quickly react to give the doc tor key portions of the equivalent of many consultations with other physicians. It will call out questions and possibilities our physician may not have considered. It will give statistical probabilities. It will have the amassed data to do so, of the relative effectiveness of various treatments with numerous variations, and warnings to account for corollary possibilities and complications. All of this will be automatically turned up by the machine, triggered by the specific, detailed data that the physician introduced about his patient. Notice that with diseases nationally monitored, the statistical approach to medical practice will take on an entirely new stature. Cause and effect relationships will be studied on a large and rapid scale, tying ailment to treatment. And again, the system will raise the intellectual effort of the users, the physicians. Missile design. The engineering field has already been revolutionized by intellectronics. The intercontinental ballistic missile would today be many years away if we had not extended the brains of the designer by electronics. Thousands of flights would have been needed in a clumsy trial and error approach. Instead, mere dozens of actual flights have been sufficient to finalize the engineering and prove out the design. The thousands of flights took place in the simulation laboratories, and the selection of the right combination of design parameters out of the myriad of possibilities too huge a task for human comparison and sorting alone was made by a man-machine partnership. Library organization. We observe that one of the things we can do with electronics is to create a library of information that is both mammoth and yet almost instantly accessible. But the memory extension is far from the total effect. The properly designed artificial intelligence works on the library's information. It has built into it a set of logical rules chosen by the human partner. With this logic, and with the information in its memory, the machine can handle the low intellectual tasks of the first sorting, the categorizing, the comparing, the selecting, and the presenting. These tasks, done well, require typically that tremendous volumes of data be processed quickly. The machine member of the partnership does this high quantity, high rate part of the intellectual job, allowing the higher intellect of the human partner to concentrate on the more subtle, less predictable, less routine aspects, the conclusion, drawing, decision-making, judgment phases of the intellectual task. Money and banking. Take money and banking, and the obliprix of keeping track of who owns what, where it is, and who owes whom. How absurd that for this kind of work we still have millions of people engaged all day in putting little marks on pieces of paper, reading THCM off, entering them without much need for deliberation in the process. Most of this is as unsuitable or the human intellect as pulling huge stones to build the pyramids was for human muscles. Someday currency and coins will be for the rural areas. Even checks and most other forms of today's original records may become extinct. If you buy a necktie or a house, your thumb before an electronic scanner will identify you, and the network will debit your account and credit the seller. The system will automatically do the routine accounting and will call out any problems in the transaction. Of course, occasionally, a transistor burning out in Kansas City may accidentally wipe out someone's fortune in Philadelphia. There will Continue to be some dangers and risks in life in the period ahead, although many will likely be new ones. Reservations. How about the making of reservations, airlines, hotels, and the like, and the waste in human intellect, tool capacity which is entailed in this increasingly important aspect of keeping the operations of the world going? In the future, we should be able to step up to a telephone-like device and, after consulting something much like a telephone book, dial a reservation request. The instrument will respond by giving a no answer, or will display alternatives that are available, or indicate an acceptance of our request. It will print out the ticket, automatically charging our account, avoiding errors, confusion, disappointment, and poor use of available accommodations. So far as technology is concerned, there is nothing about the library or the money or banking or reservation problems that requires any new invention in pure science for the application of intellectronics. It does take a great deal of engineering to achieve any one of the specific advances we might cite, and we apparently can do without any given one today. However, in each instance, we see that the increased volumes and rates, and, again, the interactions and complexities of our growing information-controlled world are pressing for new systems for handling these intellectual processes. Control of moving things. It is hard to find a better example of the urgent need for man-machine, intellectronics partnerships to handle thinking tasks than the control of things moving in the sky and even on the ground. It is clear that a human brain unaided, whether that of a pilot, an airport controller, or a Los Angeles automobile driver, cannot integrate all of the changing, dynamic, split-second facts to make decisions leading to the smoothest, safest, maximum use of a traffic artery. Intellectronics measurements are needed instantaneously on the nature, quantity, rate of change, spatial spread, and interrelation of traffic. Automatic predictions then need to be made as to consequences, and directions issued to control the flow. Not only will the handling of airplanes and the role of the pilot be drastically changed with time, but it is not completely ridiculous to imagine automobiles of the future which go on electronic control as they enter a crowded, speedy freeway, the driver limited to push-buttoning his chosen exit. Computers and automation for July, 1% 1. W. Lion. Sibylle. Arise. Lenge. Chal. Oppo. To Soul. WL. There. Logic. The T. Otic. Science. Tech. Krias. With. Quit. Errati. Shan. Tekl. To D. Kind. Fronel. Ability. Sissy. Getty. Offsp. Shack. Ti. Fact. Coor. The. Logic. Doin. Mit. Lies F. That. Ni. Psi all. Bika. Pen. S ill. Thin. Bet. Or I. T. Ing. Lag. That. TRCL1. Stro. Do. COL. S used. Gauge. Fields. Lether. Ltians. He file. luring, the layout, the npiler, iskying, process, ipiler, algian, tuits, lpilers, which, get, multi, it the, lsr, gauge, I used, choir, pilers, lermit, code, hr, table, nb, f the, entage, to a, the, bubble, t lets, e has, ars, nga, great, ctsa, blem, the, chine, lan, trans, con, piant, ie of, one can, yis, dot il, management. The average business can shift between profit and loss positions easily, by just raising or degrading the information available for decision-making by management. We are working on management control (SYS) terms in which information as to what is happening will be electronically compared with the plan. Deviations will automatically produce directives for changes in operation in accordance with stored logic set in by management to cover many possible situations, or the system will call out warnings when the unexpected happens, to the higher intellect of the human supervisors who are kept free for the unpredictable, more difficult, non-recurring situations. This is the same as having additional and more knowledge-able managers, and it also helps toward the goal of putting management on a scientific basis. Language. Clearly, most of the physical operations of the world, such as production, transportation, communication, are candidates for passing under Intellectronics SYS TEMS control. It is also significant to note that many of these operations involve worldwide integration and interconnection. In the coming years, many millions of human beings and their extensions in the form of electronic devices with electronically coded information will be increasingly in direct contact with each other across the world's language barriers. No wonder. One of the most interesting intellectronics areas in which we are engaged is the automatic translation of natural languages. Again, the machine member of the team provides the crude first cut. It also identifies double meaning possibilities and weighs the alternatives based on what has preceded. It assists and sets up for the more brainy human partner, and the combination turns out a far better performance than either alone. The concept of what language is will probably change drastically in the years ahead. The machine partners in the universal electronic systems of the future will want the facts and the rules in the most efficient form possible. They will create pressure for a universal, purely informational, completely logical and consistent kind of language. Natural languages, with their origins in earlier non-technical ages, do not satisfy all these conditions. The technological, intellectronics period of the future may force on the world a new kind of language reform. Education of human brains. The most truly intellectual activity of all must be the education of the human brain. Now, we are approaching a crisis in education because, while the needs of the more complicated, more populous world are increasing rapidly, our ability to place human Sources behind the educational system is apparently decreasing. But an intellectronics system could make a tenfold change in the effectiveness of education. The human educator can have tools analogous to the physician's X-ray machines and electrocardiographs. The routine material can be machine presented, leaving the more difficult concepts for the higher intellect of the human educator. Programmed machines can stimulate thinking of the student. An electronic presenter can speed up or slow down, add more explanations, skip. Computers, I1LD Automation 4. July, 1961. Steps, even as it makes the presentation, all as a result of continually noting the student's push-button responses to questions and then automatically changing the material or its pace to correspond to the student's apparent comprehension. An intellectronics system can be built to remember the progress of any number of students, even in the millions if that is desired. It can compare their tested learning with the plan. It can measure and report deviations. Yet, that same system can immediately recognize an individual student and give him an AC, seal-rated or other special presentation or test, all by a virtually instantaneous scan of his record and by following rules that have been set in by the wiser human educator. When the educator discusses a student's progress, he can have before him broad records of plans and performance for that student, as well as complete statistics on much of the whole educational process. Such a future educational system would involve new large industries employing experts in the subjects to be taught, in the design of programs, and in the design and production of the devices and the systems. There will be new professional groups within an augmented educational profession to provide for statistical study and planning, diagnosis, and generally for the matching of the synthetic intelligence of the machine with the human brain to achieve the fullest utilization of both in an educational system really suited to the coming technological age. The human educator will be able to rise to a higher level of intellectual endeavor, relieved of much of the volume of routine intellectual work so much a part of the teaching profession today. Military command. In assuring the defense of our nation, it is some years now since the first priority was to create the force, exemplified by the bomb, to provide the necessary military might for defense purposes. We now are already passing through the next phase, where we are providing the capability of delivering the force wherever it is needed on any part of the Earth's surface in a very short time. The coming, urgent, highest priority area in the application of technology to the military is in the intellectual aspect of the military problem in control and command, observation and communications. In a world in which one nation can inflict decisive damage on another in a few minutes, even though they are separated by half the earth, sound military action requires knowing what is going on everywhere. And this tremendous amount of diverse, confusing, and continually shifting warnings and other information must be put together into sound conclusions ready for major all-out decisions, with minor ones made automatically and rapidly in accordance with some pre-arranged plan. A man-machine, intellectronics partnership is the only answer in sight to this problem. Brain power. In the world ahead, brain power is going to be the secret of success, the source of stature, of adjustment, of security, whether for nations or for the world as a whole. but brain power in the future will clearly be recalled as the sum of natural human intelligence plus electronic intelligence. And that nation will be most influential and secure in the future, that has the greatest total of developed brain power. This means the maximum development of its natural human intelligence and the greatest exploitation of science and technology to produce synthetic intelligence. There is a snowballing effect here. The greater the synthetic intelligence, the more it will help to develop and increase the usefulness of natural intelligence. The greater the human intelligence, the more certain we will be to have the highest state of development of the artificial intellectronics systems, and the better will be the match. So far, we have seen some major technological possibilities of the society of the future in relation to certain specific functions. It is time now to widen our view and look at what some of the consequences might be in some of the broader aspects of life, freedom and democracy, international cooperation, our understanding of the universe, even art and music. Perhaps just to mention these words suggests a presumptuous departure on my part from the narrow and more proper goal I set for myself as a technologist at the beginning. Yet, the next remarks are not really inconsistent with the desire to keep my comments to my special field. It is simply that it may be of aid to those who are skilled in these other fields if some points are offered by the technologist for their consideration. Not a regimented future. To start with, we have the problem that as a result of the preceding description some may take away with them one very wrong impression, namely, that the world of the future will be an automated, robot-like, regimented world, with man even though the controller and originator no more than an anonymous cog. The world will be one in which freedom, democracy, the creative spirit, all such concepts will be pushed into the background as a mad complex of men, machines, communications, and vehicles acts to produce, move, and keep track of everything that makes up the material aspects of life. Greater democracy. I want to stress that this is not only an unnecessary consequence, but that it is an unlikely one. Let me use another example, one which is certainly an exaggeration to prove a point, but which, as with all of the previous examples, has a technologically valid basis. Suppose we want to achieve the greatest possible participation by the people of the world in determining plans and policies. We want greater democracy. We want to ensure that we are all occupied with thinking about the issues that control our lives. Now, imagine that the deliberative bodies, the congresses, of the world are exposed to every home continuously by a special television-like unit. Suppose also that it is the practice in the technological society of the future for a large fraction of the issues to come up for a vote, not just by the Congress, but by the people. For emphasis, let us imagine a somewhat extreme situation, doubtlessly beyond either practicality or desirability, in which it is the custom for the registered voters several times a day to identify themselves to the home voting machine, with their scanned thumbprints, and to put in a yes or a no, or a vote for A, B, or C. The national system then automatically registers, checks, adds up, determines, and immediately announces to the nation the majority viewpoint. Clearly, the highly technological society of the future can One in which communications are so widespread and efficient that frequent voting is easy, participation is virtually guaranteed, interest is heightened, and apathy and ignorance are virtually eliminated. In short, to those who are skilled in political science, it is worth suggesting that one of the characteristics of the technological society ahead of us is that we can have as much participation by the average citizen in the affairs of the world as we choose to have, within the limits of his interest in the issues technology makes possible, obviously, more than any practical arrangement of society will permit us to use. After all, we could not operate stably if too many voters OS dilated from day to day in their choice of chief executive, something which technology makes possible, but which is hardly acceptable as a political reality. International cooperation. By the year 2000, the pressures must certainly be enormous for international cooperation on a scale that we cannot hope to detail today, and those who study world social forces will want to give new emphasis to the technological aspects. We have previously pointed out the pressure that the machine partner will create for uniform language, at least language as it applies to information transmittal to keep the world's operations going. As another instance, we have already become reconciled to the increasing traffic in the skies and in space, both in numbers and in speed, and to the need for worldwide navigation and traffic control, if the situation is to be an orderly one rather than a nerve-wracking one. Weather control. As a future example, we can hardly imagine a worldwide weather control system, unless indeed it is one that involves world cooperation. Picture a SYS-TEM involving simultaneous measurements at many places on the Earth's surface, in the atmosphere, and out in space, recording all of the important quantities, such as pressure, temperature, humidity, winds, RA, diatustion, required to predict weather. All of this information is brought to central points, where it is computer processed, with the aid of mathematical equations based on past weather conditions, to provide up-to-date forecasts. These forecasts are then fed into another part of the intellectronics system where decisions are made, some automatically and some by the human partner, on what to do about the weather. Energy and matter are then released at various points on the surface or in the sky in order to alter the weather to something that will be different from and better than that which the system tells us would otherwise occur. But all weather interacts. Increasing the rainfall in the Sahara Desert, for example, may adversely affect the weather of Canada or Mexico. Clearly, we need not only technical cooperation, but cooperation by governments to arrange for common goals and rules of operation. Communications. The situation is not unlike the need for having an integrated telephone system we long ago saw in the Computers and Automation for July 19, IL. A 111. Sork. EasyTC. The D. Into TL. Called. Long. Tral. Takes. ComF. The. Hey. Is my. There one. That T. Gauge. Temptl. S. Let. Advan. Ingli. Kali. Large 5. Have. Large 5. Gauge. he, Ingli 5, Putin, comp, words, but, itch, stricty, choir, 4e, called, basic, unique, ama, persol, word 5, bico, to spe, to pound lv, wid, comr, simple, down, by us, and, high, binet, C01 \11, INE, IE re, car, N111, show, with, pro, LT the, gram, IPEO, TH42, G the, lental, hours, 86%, Perry, Eport, defer, teach, that, form, cheng, W re, and, with, back, I, R, loosed, novel, the, but, running, pi is, into, renize, redant, teamy, NMED, laser, stroke, Lupton, 724, redant, find, pro, t-just, dot ather, 10 old, come, more, erical, time, inning, I, 61, comma, United States that we could not hope to develop a practical large-scale telephone system if we had differ and telephone companies competing in the same area. The average business or home in such communities would have had to have a different telephone for each system. The answer was to provide for integrated, government-monitored common systems. Indeed, COM. Munich-Li-Ions is a continuing example into the future. The very extension of worldwide telephone service by way of space satellites brings into play all of the problems of arrangement, making the job of government chairmaning to decide what shall be done, who shall do it, and who shall run it when it has been brought into existence. And again, international agreements are involved. I have already noted that in the intellectual professions an electronically accessible library of information can step up greatly the quality and speed of effort. Here too, intellectronics presses for wider and wider interconnection, so that, finally, what may be desired are means for interconnecting the separate libraries of the individual countries, and even perhaps for all countries to be able to tie into a United Nations repository of facts, statistics, and records. Progress towards more accurate concepts. With intellectronics bringing rapid, yet mammoth, quantities of statistical information to bear on the operations of the world, the result is that those operations become more scientific. They are less speculative. It becomes possible to be more exact and quantitative about everything that is under consideration. Moreover, automatic processing requires that we pinpoint the logic behind our actions. The impartial, purely logical analysis that must precede the use of intellect Ronnie CSSYS TEMS should therefore lend support in many cases to those who are working toward new and more accurate concepts. Either the field is medicine or law or engineering or, indeed, government itself, intuitive feelings can be replaced by facts and analysis. and lorry over, the systems to some extent. Our self-criticizing, inconsistencies in operations may be disclosed by the very systems that attempt to ensure consistency. They automatically may show us where we must make changes in our ways of doing things. The year 2000. Let us grow bolder in a final view of the relationship between the new technology and the social forces of the future. What will be our feelings in the year 2000? About the goals of mankind, about what constitutes happiness and security, about the definition of free. DOM. On one hand, man will be faced with the evidence all about him of an infinitely intricate, busy, fast world consisting of a multiple interconnected neb of people, vehicles, machines, and communications. Always there will be the fear of man's being lost as a free soul. Great concern will exist about retaining freedom and flexibility, and minimizing tight rules. CL&D stiff controls. But, on the other hand, man will become conscious of the enormity of the universe. We shall be talking daily about distances between planets and between stars. The words billions of years will appear in common conversations. \VE shall be talking about traveling at speeds ngar the velocity of light, and, in detail, about computers and automation for July, 1961. The nature of life on other planets. \TVE may indeed be engaged in intensive work to decipher intelligent transmissions from outer space that we have received. In short, in some ways our life will seem to have the tendency of closing in on us, but at the same time, other aspects of life will have opened bigger doors than man ever before looked through. Perhaps to depict the infinite detail of our existence on the one hand, and the enormity of the unconquered vistas on the other, music and art will ask for more dimensions. \I\TE shall commence, for instance, to fill in the musical tones between the half steps. Our ears will become accustomed to increasingly detailed differences. The composer will find them necessary, the listener excitingly satisfying. A typical painting or symphony may involve almost subvisual and subaural intricacies of detail, and yet at the same time these art form must have a new gross magnitude, boldness, a new mystery, taking in the whole universe. \I face endless involvement and crowded containment, yet we shall have infinite scope in space and time. \I that a paradox for the philosophers, the artists, and the sociologists to work on at the turn of the century. Having sketched some of the technological highlights of the world toward which we are in transition, and then having suggested some of the broader, non-technical aspects which technology will influence, we are still left after this brief exploration with many more fascinating, important, and even fundamental questions. How shall we enhance, even retain, creative ITY in a world which seems to require so much coordination? How will man's incentive for accomplishment and service to his fellow men be caused, hopefully, to flourish? How do we ensure freedom to do as we please when it does not interfere with the rights of others? How do we maintain freedom of thought and true unfettered thinking in an environment of highly integrated planning? Really, all of these questions are part of bigger questions. Will the transition to the new, highly technological society be orderly or chaotic? Will socio Logical development be accelerated to catch up with scientific development. Accelerating social progress. The real bottleneck to progress, to a safe, orderly, and happy transition to the Komiji technological age, lies in the severe disparity between scientific and sociological advance. Having discussed technology, with emphasis on the future extension of man's intellect, we should ask, will intellectronics aid in removing the imbalance? Will technology, properly used, make possible a correction of the very imbalance which causes technology to be in the lead? I believe that the challenging intellectual task of accelerating social progress is for the HULENLL and not his less intellectual electronic partner. But perhaps there is a hope. If the LLIAKEENs do LLI or of the routine everyday intellectual tasks and ensure the success of the material operations of the world, man's work will he elevated to the higher mental domains. He will have the time, the intellectual stature, and hence the inclination to solve the world's social problems. We 1I1 UST believe he has the capability. 21. Readers and Editors Forum. Continued from page 6. Is to prepare to try to survive and win a war that will certainly come, sooner or later. Besides, it is better to die than to live under some conditions. 2. From the editor. I/TE value readers' discussion and argument on the controversial subject of computers and arms control. A great many ideas need thoughtful consideration before a rational consensus develops among the people. Of account try. One reader says only by the action A can we break the condition B. Logically such a statement is open to question, because it is very hard to show that there exists only one way, A, and no others for accomplishing something, breaking up B. Another reader says all C's in history have resulted in D. Therefore we can expect D, and we should adjust to that. This argument also is to be distrusted, because in history some conditions D stop. For example, human slavery has stopped, which was not true when the Constitution of the United States was written. One of the main problems of computer people is living up to their social responsibilities as computer people actions to help avoid the destruction of millions and millions of people from the use of nuclear weapons guided by computing mechanisms. Restless Giant. Walter Brandenburg. Lake Mahopo, NY. Thunk, thunk, thunk. Steel jaws clattering. Gulping cards by the hundreds. Digesting every perforated fact. Keep that hopper full. Not a minute's rest. Swish, swish, swish. Like an angry python. Darting in amongst the whirling discs. Striking with deadly precision. A miss would be tragic. Not a second's rest. Whir, whir, whir. Load that tape. Characters by the thousands. Reels twitching nervously. Tape quivering with tension. Not a millisecond's rest. Flip, flip, flip. Cores switching row on row. Hysterically pursuing the elusive flux. Memories from which to pick and choose. Following tortuous windings to a random byte. Not a microsecond's rest. 22. Think, think, think. Bits, bytes, characters, and words. Records variable and fixed. Serial, parallel, random data pouring in and out. Calculations by the millions. Not a millimicrosecond's rest. Hum, hum, hum. Rolling on with high-pitched whine. Spewing out broadsides of magnetic moment. Heads gliding along on flying disks. Minute ripples and sinus currents. Not a microsecond's rest. Clatter, clatter, see elder. Cascades of rippling paper. Rows of hieroglyphics. A language called computers. Keep that paper flowing. Not a millisecond's rest. Kerchunk, kerchunk, kerchunk. Angry teeth biting a new pattern. Checking it when all is done. Spitting out chips that have no further meaning. Tiny windows shedding light on the unknown. Not a second's rest. Watching, watching, watching. Anxious eyes their vigil keep. Time is such a trifle deci, milli, micro. But the cost is astronomic centi, kilo, mega. Pushing bulletins, throwing switches. Not a minute's rest. T. I. Walter Brandenburg. Calendar of coming events. July 13th to 14th, 1961, Conference on Data Acquisition and Processing in Biology and Medicine, University of Rochester, Rochester 20, NY, contact Kurt Inslane. DIR of Research, Brooks Research Incorporated, 399 WCOM. Merschel St., P.O. Box 271 E. Rochester, NY. July 16 to 21, 1961, 4th International CONF on Medical Electronics and 14th CONF on ELEC. TECH in Med and Bio. Waldorf Astoria Hotel, New York, NY, contact Dr. Herman P. Schwann, University of PA, Moore School of Electrical ENG, Philadelphia 4, PA. July 21 to 22, 1961, Northwest Computing Association. Annual Conference, University of British Columbia, Vancouver, British Columbia, CAN, contact Conference in Formation, Northwest Computing Association Box 836. Seahust, Wash. August 22 to 25, 1961, Weskin, Cow Palace, San Francisco, California, contact E.W. Harold, C/O Weskin, No. California. Office, 701 Welch Road, Palo Alto, California. September 4 to 9, 1961, Third International Conference on Analog Computation, organized by the International Association for Analog Computation and the Yugoslav National Committee for Electronics, Telecommunications, Auto Machine and Nuclear Engineering, Belgrade, Yugoslavia. September 5 to 8, 1961, the First International Conference on Machine Translation of Languages and Applied Language Analysis, National Physical Laboratory, Teddington. Computers and Automation for July, 1% 1. Medic. Crow. Turns. Daub. First I. Other. Th. With. In ELE. Aspo. AT. Book. Way. Infone. ERSU. Shins. The. Pros. NAR. Answ. Renel. The essay. Make. To th. Th. Scroll. Calls. Has h. A pro. GLEFR. Roll 0. The E. Stano. Thick. 4J. WI. Tain I. The K. SPMS. Pose. Turn. Venal. MOVL1. Of rig. Serta. TH. This IL. And R. That one. Now. Packed. TH. Main. Training. Clear. Bin. TH. Proic. Skin. Cons. That T. Then. Co2. Sum. Elma. E2. Well. T this. Fully. N1ZA. Wanda. And. Idea. Earn. Shin. All. Ever. Wanda. Siri. Dot ends. LS or. Must. Pro. Netty. Reis. E2. The. Of. NTS. G in. Con. Did. Stu. LS he. In. Gaps. Pre. Lickle. I. Res. T us. Rith. %1. Middlesex, England, contact Mr. John McDaniel, N.A. National Physical Lab, Teddington, Middlesex, England. Teddington Lock 3222, EXT 138. September 5–8, 1961, 16th National Conference of the Association for Computing Machinery and First International Data Processing Exhibit, Stadler Hilton Hotel, Los Angeles, California. Contact Benjamin F. Handy, Jr., Gen. Chairman, Litton Systems, 5500 Canoga Avenue Wood. Land Hills, California, E. Floyd Sherman, Exhibits Chair. Man, Control Data Corp., 8421 Wilshire Boulevard, Beverly Hills, California. September 6–8, 1961, National Symposium on Space Elec and Telemetry, Albuquerque, NM, contact Dr. B.L. Bassor, 2405 Parsifal, NE, Albuquerque, NM. September 6–8, 1961 Annual Meeting of the Association for Computing Machinery, Stadler Hotel, Los Angeles, California. Contact Benjamin Handy, Chairman, Local AR. Rankments Committee, Litton Industries Incorporated, 11728. W. Olympic Boulevard, W. Los Angeles, California. September 11–15, 1961, the Third International Congress on Cybernetics, Namur, Belgium. Contact Secretariat of the International Association for Cybernetics, 13, Rue Bas Marcel, Namur, Belgium. September 11–15, 1961, ISA Fall Instrument Automation Conference and Exhibit and ISA's 16th Annual Meeting, the Biltmore Hotel and Memorial Sports Arena, Los Angeles, California. Contact William H. Kushnick, Exec. DIR, ISA. 313 6th Avenue, Pittsburgh 22, PA. September 24–26, 1961, International Congress of Automation. Turin Polytechnic, Turin, Italy. Contact Secretary, International Congress of Automation, 1, Piazza Belgioioso, Milan, Italy. October 10–13, 1961, Use Meeting, Warwick Hotel, Philadelphia. Delphia, PA. Contact J.W. Nikitas, Seki, Use, Rem. Ington Rand Univac, 315 Park Avenue. So, New York 10. NY. October 11–13, 1961, Conference on Application of Digital Computers to Automated Instruction, sponsored by System Development Corp and the Office of Naval Research, Department of Interior Auditorium, CST, B. Between 18th and 19th STSNW, Washington, D.C. Contact Washington Liaison Office, System Development Corp., 1725 I Street Northwest Washington 6, D.C. October 12 to 13, 1961, the UNIVAC Users Association Fall Con. Ference, Warwick Hotel, Philadelphia, PA, Contact Wall. Ter Edmiston, Seki, UNIVAC Users Association, Philadelphia. Naval Shipyard, Philadelphia 12, PA. October 25 to 26, 1961 Computer Application Sympo. Some, Morrison Hotel, Chicago, Ill, Contact Benjamin Midman, CONF Program CHM, Armor Research Found. Dashan, 10W35ST, Chicago 16, Ill. October 3, 1961, 8th Institute on Electronics in Management, The American University, 1901 FST, NW. Washington 6, D.C., Contact Dr. Lowell H. Hattery. DIR, 8th Institute on Electronics in Management, The American University, 1901 F. St. NW, Washington 6, D.C. December 12 to 14, 1961, Eastern Joint Computer Conference. Sheraton Park Hotel, Washington, D.C., Contact Jack Moshman, CEIR, Inc., 1200 Jefferson Davis Highway. Arlington 2, VA. Opportunities in Electronic Data Processing. Auto-coding. Site Representative. Technical Writing. Systems and Sales. Customer Site Representative, locations will vary. Qualifications require broad experience in programming, operation, and systems analysis. Must have worked with tape systems and be familiar with computer user problems. Training given at Dayton prior to installation assignment. Sales support, at least 2 to 4 years of programming experience. INS plus BS or MS in Business Administration or Mathematics. Opportunities include, programming, manual writing, systems analysis, research, instructing. The national line of EDP systems including the 304, 315 and 310 provides the basis for interesting and effective work in any operation wherever money or merchandise is handled. Stability and growing responsibility are characteristic of the climate at national whether your work is in centers, New York, Dayton, Los Angeles. National's newest contribution to the business field is its modern and complete data processing centers. These centers, no matter where they now exist or where they will exist in the future, answer the everyday needs of the small or the large business in the area of electronic data processing. To fulfill this function service to business we need men of above average ability who are trained and experienced in tape system computer programming or operations. In most cases a college degree is preferred. One of our data processing centers or with our data processing systems and sales group in support operations. General qualifications for present openings are a college degree and experience with the tape system applied to business or financial functions. If qualified and interested, please respond promptly and in complete confidence. All qualified applicants will receive consideration for employment regardless of race, creed, color, or national origin. Right to T.F. Wade, Technical Placement. The National Cash Register Company, Main and K Streets, Dayton, 9, Ohio. Asterisk trademark reg. US Pat. Off. Asterisk. The National Cash Register Company, Dayton, 9, Ohio. One of the world's most successful corporations. 77 years of helping business save money. COL/Iputers a 1/D/ automation for July, 1961. Electronic data processing. Adding machines. Cash registers. Accounting machines. NCR paper, no carbon required. Who's who in the computer field. A full entry in the who's who in the computer field consists of name/title, organization, address, /interests, the capital letters of. The abbreviations are the initial letters of applications, business, construction, design, electronics, logic, mathematics, programming, sales, /year of birth, college or last school, background, year of. Entering the computer field, ACU. Potion/other information such as distinctions, publications, etc. An absence of information is indicated by hyphen. Other abbreviations are used which may be ESIIY. Guessed like those in the telephone book. Every now and then a group of completed whose /YHO entry forms come into us together from a single organization. This is a considerable help to a compiler, and we thank the people who are kind enough to arrange this. In such cases, the organization and the address are represented by 3 dots. Following are several sets of such /YHO's who entries. The Babcock and Wilcox Co. Research Center, Alliance, Ohio. Ralston, Edward L. /Apple's Repair. /A/20, Columbia University 55. Tamanaha, Hydco Miss 1 PRGMRO per. /P131, John Carroll University, 58. Burroughs Corp., Electrodata Div, 585. University St. Montreal Ave, Montreal. K. Baudot, John A/Tech Repair. /amp. /29, McGill University, 56. Scully, George V /Compare Specialist. 1S/18, McGill University, 56, Cell E1 Ecn. Digcom Systems. Computing Center, University of KY. Hamblin, John W. /dir. /amp, in. Struction 124, Indiana University, Per. Du University, MS, PhD, 56, CTR. Administration and Consultant. Lots, Carol J. /Moxup. /ABP1. 31, University of Louisville, University of KY, 58. Moxup. Navarro, Silvio 0/Assistant DIR. Adolp 127, University of Houston, BS. Texas A&M, MS, PhD, 56, Residential and Teaching 1 Fast PRGMGSYS, a format. Dress to Soap, translator for IBM 650. Tarpey, Paul R1 Data PRCG Chief. /HP, Instruction 133, Oklahoma ST. Uli /BS, FS, 59, Data PRCG Chief. Hospital Service Association of Western. 1, 01, Union Trust Building, Pittsburgh, PA. Kilg, Dewey 1 PRGMR. 1 ABP/29. Uni of Pittsburgh, 57, Systems Analyst. PRGMR. Supplement. More, Jones/PRGMR. /ABMP/36. University of Pittsburgh, 58, Systems Analyst. PRGMR. Schuler, Robert/PRGMR. /ABP/. 35, University of Pittsburgh, Grad. School, 59. 57, Systems Analyst, PRGMR. Zach, William W/MGR, Elect Data. PRCG. /ABP/30, University of Pitts. Berg, Grad School, 59, 57, Systems Analyst, PRGMR. Imperial Oil Limited, 300 9th Avenue West Cal. Gary, Alberta, Ken. Hodson, Bernard A/PRGM Analyst. /MP, Lecturing/28, Manchester University. 55, Math/PubShed Paper on Gas Turbine DSN, 1 Royal Aeronautical Society Award. Kemp, EM/PRGM Analyst. /BP1. 34, University of Western Ontario, 59, Ingr. Logistics Systems Development Section, SYS. Thames Development Branch, Statistical Services DIV, Comptrier, Ogden Air Ma. Material Area, Hill Air Force Base, Utah. Painter, Dean C/MGM Analyst, DIG. Contra Systems. /ABCP, Systems. Design and Analysis for Business LGM and Logistics Systems/25, Weber Jr. Coley, 55, Systems Analyst. Plant, Thomas E/MGM Analyst, DIG. Contra Systems. 1 ABCP, Systems. Design and Analysis for Business RGM and Logistics Systems/29, University of Utah. 56, Systems Analyst. Pomeroy, Charles E/MGM Analyst, DIG. Compare Systems, PROJ Ofcr. /ABP. SYS Design and Analysis for Business MGM. Uplands and Logistics Systems/23, University of Utah, 55, Systems Analyst. Minneapolis Honeywell, Datamatic DIV. 1825 Connecticut Avenue North W, Washington, D.C. Crawford, Lyle C/Uplands Analyst. 1. UB/32, University of Arkansas, 57. Findling, Irwin H/Methods Analyst. 1 UB, Retail Uplands/33, New York University, 56, Systems Analyst. Kirkland, Byron E/Methods Analyst. /ABPS, Graphic Aids to EDUC in the Compare Field/32, Strayer College of Accountancy, 54. Loveorn, Homer B., Jr., /Methods Analyst. /ABP 132, Georgia Tech, 58. Methods Analyst. Mullinax, Roy Paul /Methods Analyst. /AMP 128, Furman University, 53, Systems Analyst. Thompson, Sam H/Methods Analyst. 1S/35, University of Tennessee, 7 greater than 7. Methods Analyst. The National Cash Register Co., 50 Rock Feller Plaza, New York 20, NY. Fokins, Henry /MGR, Elect Mock Sales. /ASP114, State Teachers Call of NJ, 55, Elect Mock Sales, NCR 304. Hunt, Frank J. 1 Sales Repair, Elect Mock Sales. /APS/17 Pace INST, 58. Elect Machine Sales, NCR 304. Istam, Walter E. 1 Apples Repair, Elect Ratch Sales. /APS/34, Stevens. JNST of Technology, 55, Elect Mock Sales, NCR 304. Rude, John F/Applers Repair, Elect Mock Sales. /APS/30, Seton Hall University. 55, Collect Mock Sales, NCR 304. Seger, William T/Apples Repair, Elect Mock Sales. /APS/31, Stevens. INST of Technology, 57, Elect Mock Sales, NCR 304. RADC, Rome, NY. Rotto, Richard/Mathen. /PM/35. Utica Coil 7 greater than 6, Mathen. Squire, Clark/Mathen. /PM137. Prairie View A&M College of Texas. 56, Mathen. System Development Corp., 2500 Colorado. Abe, Santa Monica, California. Brown, Kenneth W/PRGMR. /LMP1. 35, NC State Coil, 59, PRGMR. Cotman, Norman C., JR/Compare PRGMR. /Ablum/28, UCLA, 58, PRGMR. Fearing, Edward A/PRGMR. 1 ABLP. 132, University of California, 58, PRGMR. Fletcher, James M/PRGMR. /LP/. 28, Compton, Coil, UCLA, 56, PRGMR. Jackson, WMR/PRGMR. /P/25. University of MO, 50, PRGMR. McVeigh, Douglas H/PRGMR. /LP1. 31, San Francisco State Coil, 59, PRGMG. Feelink, Nicholas/PNRMR. /ABP/. 35, University of California, 59, PRGMR, Analyst. Pont L, Gloria J/PRGMR. /LP. 39, Purdue University, 59, PRGMG. Tosh, Catherine E., MRS/PRGMR. /LMP/33, UCLA, 59, PRGMR. Texaco Canada Limited, 1425 Mountain Street. Montreal K. Kerr, Douglas, JR/PROC Ingr. /ALMP. 133, McGill University, 58, PRGMG Consultant and Analyst. Lokes, Robert B/PROC Ingr. 1. ALMP 133, McGill University, 58, PRGMG. Consultant and Analyst. Abrams, Walter G/Systems Analyst. PRGMR, U.S. Army QMCORPS. Yuzakmsk. Box 31, APO 169, New York. NY/ABP 132, Georgia LNST. Of Technology - Military Officer, U.S. Army. Addis, Roland Tires Analyst, Howard. Savings in Stun, 251, Plain Street, Newark. NJ/AP, Elects in Banking 131. Dartmouth, 57, Residential Analyst. Agib, Edward G1 MGR, Product 1 LNG. Monroe-Lytton Industries. 555 Mitchell. St, Orange, NJ1 Abdib/22, University of Lausanne, IE, 45, Switz, 47, Department. MGR, Ingr 1 author several reports on automatic ECM for toll RDS and toll systems. Anderson, Robert F1 Branch MGR, Min. Neapolis Honeywell, 1825 Con AC. Washington, DC 1 as 127, MIT, I2. Sales MGR. Beaton, UR/Staff Ingr, Construction de / Engineering Department, EI DuPont de Nemours. & Co., Wilmington, Dell 1 ABP, Systems. Desnai 26, Harvard, 154. Bellin, Edward F/Sapir, Communications and Maintenance, Telecomputing Corp. Engineering Services DIV, P.O. Box IG1H. Vandenberg AFB, California 1 Actal, Re. Mote Operathon and Input 122-53. Select/Desn EDP Systems and Supple. MNTRY Devices. Belser, George R1 PRGMR, Commodity. Credit Corp, 4706 Motley. Mescasi. Computers and AutoIt for July, L. IL. Progr. Then. As. The 41. Use TL. These. Of up. As. A spy. The F. Ing. Already. Have. O. Henri. Houn. Ans. 10. Th. Cham. Hi. W. Div. Ibivi. Tem. Ina. With. // Send. Gray. BL. Read. A. Then. Prod. Secti. Of TH. TL. Patel. Cases. Card. FR. To D. Com. Asker. In TH. Forn. Free. We I. Com. R. C0111. IIPT. We see. If. PLite. USTL. 4. Zinc. All. C. I. Ben. N. In as. Hout. Used. List TI. Duce. It is. R of. The. Eco. Ug. TT2. Isel. Lshuel. RB. May. Trust. L4. N. Miss. T in. Tlas. And. Red. LCED. Dis. Enter. Equals : alley. And. Tory. G in. Day. Sage. Ket. Mal. N. Len. 1 re. Tory. 1961. Rec/P, Quality Contract of Compare Alt. Put/2s, University of Tex, 58, Ectunt. Birch, Louis JJR/Com Group. Leader, So California Cooperative End. Tunnel, 950S Raymond, Pasadena, California /FP/32, Los Angeles. State College, 54, Comg Analyst. Chesis, Sheldon/Methods Analyst, in. Neapolis Honeywell Regulator Co., De. Tomatic DIV, IS-25 Con Ave, Vashing. Ton, DC, /FP/34, George Wash. Ington I. Janav, 57, Methods Analyst. Cooley, Elierson F/dir Methods Re. Search, Prudential Inns Co. of America. Newark, NJ/ABL, Educational /Feth. OD/I, Dartmouth, 47. DiCostanzo, John A/Staff Ingr, IBM. Corp, Kingston, NY/ADPR, SYS. Tem Testing/28, Holy Cross College. 55, PRGMG Project Coordinator. Drove, Charles CV/Senior Systems. Analyst and Compare PRGMR, Compania. Shell de Venezuela, Apartado 19 Mara. Quejo, Venezuela/ABP/20, Uni. Versity Europe, 56, Economist. Duke, Mrs. Jane Thomas/Dig Compare. PRGMR, Commodity Credit Corp., 500S. Hervé St., Dallas, Tex/Alp/20, East. Texas State Teachers College, 58, Dig. Compare PRGMR. Ehrenherg, Dennis F/Compare PRGMR, at Atlantic Fitupkin Center, Synclant, Nor. Folk 2, VA/ABP/34, Univaxi. Entific 1L03A Systems Operations. Training, 59, PRGMG, USIL. Fagan, Albert A/Prez, State Sound Serve. ICE, 17, West Magnolia Street, California /ACE/I. Latest ILJ Rovman TS Elect Control / 99, have not stopped red going to school. 59, Installation and Maint Gen L Opern. /member IR, AES, S:/IPTE, Nuclear. DIR AIM, Who's Who in California, Who's VHO in the V-Vest. Fiedler, Joseph/Association Ingr, IBM Fed. Errol Systems DIV, CPO Box 120, Kings. Ton, NY/ADEMP, Analog Compare. AFIS/5, CCNY, Columbia University, 47. Ingra Analytical Techniques Group, SYS. Thames DIPL/Talk at Eastern Simulation. Council, 1059ths, on an automated data comparison procedure for an analog computer. Fleming, Jim/Dig Compare PRGMR, Com. Commodity Credit Corp., 12007, Gator Drive. Mesquite, Tex/Alp/30, and Tex. State, 5, I. Phonisksa, John R/Department Head, Banking. Inns, Henri, J. /Luhawk Valley Techl. INST, Utica, NY/P Education/25. Harvard Law - Coley ADM. Freefield, Rowena W/Dig Compare. PRGMR, Commodity Credit Corp., 500S. Hervé, Dallas, Tex/BD, Transptatun. And Traffic MGMFIS and Systems. Desn/17, Southern Methodist University. 57 FRT Traffic Offgr. Fretz, William LJR/Sapir, Analysis and Pergming, Data Proc Section, Westing. House Atomic Power Lab, PO Box 1526, Pittsburgh 30, PA/ABP/29. 47, Opal. Gillis, James W/Ingru, Bendix Radio. APO 925, San Francisco, California /ELP. /-- Georgie, Oliver J. /Systems Reliability. Ingru, RCA, Camden, and J. /Reliability. /32, PWTINST, 56, SR Desner /Pub. List summaries on reliability, Devised new methods of component analyzing, Desn proper documenta. Shin to accept reliability in form. Gortz, James J. /Compare PRMGR, Con. Verdi IV of General Dynamics Corp. 3201, Pacific Highway, San Diego, California. /MP/34, San Diego State Coley, 59. Halbrecht, Herbert /Prez, Herbert Hal. Brecht Association, Inc., 332 South Michigan Avenue. Chicago 1, 3/AB, Personnel Re. This logic array has been developed in the Remington Rand Univac Mathematics and Logic Research Department. In simplified form, each circle represents a film element that ends the bits from the horizontal and vertical lines to produce an output on the diagonal line. The input word is therefore left circular shifted s places. In passing to the output, such matrices can produce arbitrary right or left shifts, either circular or open-ended, in a single clock period for full-length computer words. Film logic arrays open a new field of high-speed, high-density logic devices. Nowhere in the computer industry will qualified applicants find greater opportunity for both personal and professional reward than they will today at Univac. Highly significant positions involving work such as that outlined above are now available. You are invited to investigate them immediately. St. Paul, Min. O. Military Systems Analysts, Computer Programmers, Computer Logical Designers, Engineer Writers, Computer Applications Analysts. For the above positions in our St. Paul, Minnesota, laboratories, send resume of experience and education to R.K. Patterson, Remington Rand Univac Park St. Paul, Minnesota. San Diego, Cali F. O. Computer Programmers, Military Systems Analysts. O. Systems Test and Evaluation Engineers. For data extraction and reduction, debugging of equipment, and systems integration. The above positions are now available at Remington Rand Univac. In San Diego, send resume of experience and education to William Lowe, Remington Rand Univac P0, Box 6068, San Diego 6, California. All qualified applicants will be considered regardless of race, creed, color, or national origin. 7 IND, UNBUC. Division of Sperry Rand Corporation. There are also immediate openings in all areas of digital computer development at our other laboratories. Inquiries should be addressed to F.E. Nagel, Remington Rand Univac. P.O. Box 500. Blue Bowl, Pa. J.R. Stall. Remington Rand Univac. 315 4th Avenue. Now York 10, New York. Computers Al/D Automation for July, 1961-25. New Soundcraft Magna C kit. Makes magnetic tracks visible. Checks for track placement, head alignment, pulse definition, size and width. For free Magna C. Brochure, right. Dropout areas and other trouble spots. Magna C Kit. Contains, pint. Magna C Solu. Shin plastic bath. Eyepiece magnet. Fair pressure. Sensitive tape. 5 glass slides for permanent copies of tracks, and complete instructions. REAVESSOUNDCRAFTCORP. Great Pasture Road, Danbury, Connecticut. Recruitment, Department Anal. ISA/27, University Chicago, MBA, 57. MGMMNSLTNT/article for American Business, VP Go CHPTRINST of MGM. Sciences. Hans, M. William / Uppens Ingr, Prince. Ton Computation Center, PO Box 582. Princeton, NJ/AMP/28, Queens. College, 57, Uppens Ingr. Healy, Edward B. Jr/Systems Analyst. Atlantic Terminal Transit Command. 1 First Avenue, Brooklyn, NY/ABP/. 33, Columbia University, 57, Logistics. Henry, Michael J/Business Systems. Analyst, GE Co., PO Box 988 Huntsville, ALA/ABP, Engineering Documentation. /32, Spring Hill College, 54, Systems. Analyst/ published a paper, GE Techl. Inform series entitled, Parts Gen. Irration. Hessler, WMQ/Development Ingr. EDPM Programs, Western Electric Co. Hawthorne STA, Chicago 23, 3/ABP. /26, Purdue University BS, Northwestern University M-Bus Ad, 58, Ingr/Publica. Shin, Self-Initializing Counter, HA. Thorn Compute Rama, Issue Number 33, May 12, 59/Alpha Kappa PSE, ETA Kappa. New, Delta Sigma Phi. Holly, W.M. Carl Jr/Methods Analyst. Minneapolis Honeywell Regulator Co. Datamatic DIV, 1825, Connecticut Avenue NW. Washington, D.C/Alp/29, Ameri. Ken University, 56, PRGMR. Holmes, EA3/VP, Industrial Prod. UX, Autonetics, a DIV of North Ameri. Ken Aviation, Inc., 9150 E Imperial Highway, Downey, California/Abdulm/. 21, MIT, 57, MGR/MKT Ping. Horton, Dr. Thomas R/MGR, 700-7000. Systems Mting, IBM Corp., 112 E Post. RD, White Plains, NY/APS/26. University of FLA, 54. Howell, John R/PRGMR, Stat Section. AGEXPSTA, University of FLA, Gainesville. 26. FLA/EMS/30, University of FLA, Dash. PRGM Statistical Probs. Imislund, Charlotte A/Dig Compare. PRGMR, Commodity Credit Corp., 2505. Klondike DR, Dallas 28, Tech/Alp/. 29, Collar School of Nursing, 58. PRGMR. Irby, Jack G/Chief PRGMG Staff, U.S. Department of AGR, 500 South Irvay Street, Dallas I. Tech/BP/21, LaSalle, 57, Superiorson. Of PRGMG staff using 705-21 Compare. James, DL/Systems Ingr, iTech Corp. 1605, Trapello Road, Waltham 54, Mass/. Ablum/28, MIT, 53, Ingr MGR. Jones, Walter TJR/Compare Department MGR. Queen Knitting Mills Inc., 2701 N. Broad ST, Philadelphia, PA/BP/26, Drexel. INST of Tech, 58, ECTAD. Kalbach, John F/Association DIR, Engineering, Burr. Ruffs Corp., Pasadena, California/D, Re. Liability/14, University of Washington, 51. Ingr. Kinnison, Frank DJR/Techl Assistant, New. Miracle Analysis Group and Mathn. Aerojet General Corp., Box 1947, Sacra. Mento, California/29, California State Poly. Technic COL, 59, Mathn, PRGMR, Techl. Advisor. Kirby, Clifford/Sapir of Telecom. Delta Airlines, Atlanta Airport, at Atlanta, GA/AB, Gen Perp for Airline. Appearance and Residential Use/14-55, Com. Munications. Kobe, SP/MGR Radio and Teletype. Systems, Capital Airlines Inc., Washington. National Airport, Washington. DC/ADP/16, Keystone Radio. INST, 58. Kerner, Horst G/Physicist, Avco Elec. Tronics Research Labs, 750 Common. Wealth Ave, Boston 15, Mass/Adelp. Inform Retrieval/32, Northwestern University, 59, Physicist. Korsoon, M/dir of Dataproc, Shamoon. Industries, Inc., 55, Liberty Street, New York. 5, NY/Ablum/10, - 56. LaHood, Joseph Jr/Staff Ingr, Systems. Development, Bendix Systems DIV, 3300. Plymouth RD, Ann Arbor, Mich/. ALMP/30, University of Mich, SYS. Thames Ingr. Langhorne, Thomas Churchill/Systems. Reviewer, Prudential Insco, Newark. NJ/ABP/31, Citadel, Rutgers. 57. Laroche, Francis Edward/Tech Writer. Stanford University Graduate School of Busy. Ness Research Center, 560 Alvarado. Rowe, Stanford, California/Tech Writing. And editing in the comparable field/. 28, University of Mich, 54, Tech Writer. Larrabee, Robert W/Apples and PRGRNG. Analyst, Monroe C. Calculating Machine. Co. Electronics DIV, 555 Mitchell Street. Orange, NJ/ABP/30, Texas Tech. College, 53. Luck, LTCOLCEWN/DIR, Ingr Data. Proc Center, Office of the Chief of Ingrs, Washington 25, DC/ABCD. ELMP/15, Harvard, 56, LTCOL, US. Army. Martason, LTCOLWN/Officer in Charge. Systems Engineering Section, Statistical and ECT Branch, TAGO, Pentagon, Wash. Ington 25, DC/ABP/16, Ohio State. University, MBA, 59, LTCOL, U.S. Army. McCall, JC/Mathn MBR of Techl and Scientific Staff, Computation Lab, Army. Ballistic Missile Agency, Redstone AR. Senel, Huntsville, ALA/AMP/27. University of IL, 55, CivServ, Appleton of IBM. 7092 Ingring Problems, Library Sub. Routine Investigations, etc. McInnes, DP/CUST Ingr, IBM Corp. 1111 Connecticut Avenue, Washington, D.C. /Adulm/29, NC State College, 57. CUST Ingr. Miller, William F/dir, Applied Math. Maddox Div, Argonne Nat. Lab, Box. 299, Lamont, 3/DLM/25, Purdue. University, Ph.D., 55, Physicist, Math. Morton, Walter B. Jr/Project MGR, EP. SCO West, a div of EBSCO Incorp., 240E. Paulette R.D., Anaheim, California/M, Eco. Nomics/26, Carnegie Tech, Lehigh. University, 51, Elikengr. Moss, Judith/Chief, Integrated Data. PRCG div, City of Philadelphia, 802 City. Hall Annex, Philadelphia 7, PA/UB/. Dash, Vassar College, BA, Columbia University. Ma, 55. Naruoka, Masao/Dr. of Engineering, Department of Civil Engineering, College of Engineering, University of IL, Urbana, 3, Tucept, 0, Department of Civil Engineering, Yashida Hanmak High. Sakyoku, Kyoto, Japan, after Sept, 0/18, Department of Civil Engineering, Kyoto IM. Imperial University, 57, Prof of Structural Analysis, Kyoto University, Japan, Post. Doctoral Fellow in Civil Engineering, Tucept. 60/publication, on application of Digital Compare to Structural Analysis. PROC of Japan, SOC of Civil Ingres, Volume 43, Number 12, and Vol 44, Number 1, 58 and 59. Digital Compare Analysis of Orthotropic Parallelogram Plate, MEM of FAC of Engineering, Kyoto University, Vol 21, Number 2, 59. N. Azamsh, Salim J/Systems and Elec. Tronic Data Proc Analyst, Ford Motor Co., Mel Div, 3000, Schaefer Road, Deer. Born, Mitch/ABP, Installation, VC. Ability Studies/22, University of Missouri. BJ 51, Ma 54, 55, Systems and Elec. Tronic Data PRCG Analysis. Nichols, Joe E/Research Math, Shell. Oil Co., Houston Research Lab, PO. Box 2527, Houston, Tech/Abdelmp. /30, University of Houston, 56, 0 RSPE. Chalist/paper entitled An Improved Multiple Regression Analysis Program. For the IBM 650 presented at ORSA. 150th Nat. Meeting, May 15, 59. Pelletier, Hermel/Assistant Superior, Provincial Government, Department of Agriculture. Quebec. /AMP/34, Saint Jean Baptiste, Dash. Perstine, Millard H/Compare Systems. Spec, System Development Corp., 2500. Colorado Ave, Santa Monica, California /MP, Dataproc Research /25, University of California, 55, Secretary Share. Peterson, Norman D. Chief of the MA. Chine Statistics Unit, Army Personnel. Research Branch Washington 25, D.C. /ALMP, Upon to StatPsych and Operties. Res /28, State Coil of Wash, MS, 55. Math /Artle 702 PRGNG8 and Pitfalls. Comp News, July, 56, Phi Beta Kappa. Psyche. Petrover, Lothar Leopold /Analyst. Broadview Research Corp., 1811 Trues. Dale Dr., Burlingame, California /ABLP. Economics, Military ADM /31, City. Coil, NY, BA, 56, Analysis, DESN, and PRGMG Spec /MBRSOC of American Military Ingres, Reserve OFCs Association. American MGM Association. Omeroy, Richard W. Sister Consultant, Arthur. Young & Co., 165 Broadway, New York. 6, NY/ABP/22, Columbia University. MGM Consultant Contributed Chapter. On Systems Charting for Systems and Procedures, a Handbook. For Business and Industry. Prentice Hall 59. Rees, John H. /SNR Ingr, Lago Oil and Transport Co., Ltd., P.O. Box 311, Lago. Colony, Aruba, Netherlands Antilles / Appens to Technel, Industrial, Engineering Prob. LEMS, Mathel Techniques and Operations. Analysis /24, MIT, 53, Chemical Ingr. Russo, Royal /Insta in Elekengring, Pa. State University, University PK, Pa /ADL. EDUC of Logical Design Ingr /35, Pa State. University, 57, Insta in Elekengring and Logi. Cal Design Ingr. Computers and Automation for July, 1961. FO. Weighty. Tunatai. Sistel. Orion 1. Oper. Spissy. With. Ubda. Sales. Sales. Guide. Bizon. Back. Open. Or WR. Ditver. All qual. Without. COL /11. Loop. Lud. N. Lukter. B. Null. Stem. D2. Ind. Use. Level. Pre. Ind. R. Sure. 4. Low. And. That. Ian. T-Pood. Teo. Rent. Bud. Ning. Ling. Ling. Mels. Ning. Love. R. Hitch. 4. Mal. Uter. Lake. Ivety. HA. Larm. And. You. Is. Lid. That. Are. There. Ales. 1% 1. Schneider, Franz W. /Research Assistant, Math. Department, University of Chicago, Chicago 37, IL. RCA Labs, Princeton, NJ, after June 60, /ALMP/32, University of Chicago. 53, Math. Schneeduind, Nonnen/Data PRCG Anna. LYST, Title Ins and Trust C, 433S. Spring ST, Los Angeles, California/AP/28. University of California. 56, Elekengr. Schnedger, Harry F/dir, Dataproc and Systems, Beech Aircraft Corp., 9709A. Central Ave, Wichita, Ken/ABP/23. St. Louis University, 57, Dataproc and SYS. Thames. Schwartz, Jack M/Department Head, Chrysler Corp., Missile DIV, P.O. Box 2628. Detroit 31, Mitch/AD, EDP System/21, University of Detroit, 60, Ingr. Shelton, Russell 0/dir, Current Uplands. Com Department, Phillips Petroleum Co. Bartlesville, Oklahoma/AMP/24, North. Bookstern University, Oklahoma State University, 51, Chem. Ingr. Simmons, FP/Staff Scientist, Link DIV. GPI, Binghamton, NY/AD/26, MIT. And George Washington University, 50, Ingr. /patent, Polar Analog Navigation. CMPTR, Publication, Solid State Analog. Contra for Automatic Gas Flow Comps. IRINT, Convention, 3/60ths. Sparks, BW/MGR, Data PRCG Planning. RCA Missile Test PROJ, Patrick AFB. FLA/ABLM/20, Purdue University, PhD. 52, Planning Ingr. Stag, Glenn W/Head, Comparables. Section, American Electric Power Service. Corp., 30, Church Street, New York 8, NY. /ABP, Simulation Studies of Elect SYS. Tem/23, MIT, BSEE 49, NYU. MSBA, 55, 52, Comparable Ingr/ MBRLE, ETA Kappa New Award 4. Outstanding Elekengr, 57, Papers and Articles on Comparables. Stewart, William A., JR/Sector PRGMG. Leader, Detroit Air Defense Sector, SYS. Tem Develop Corp., 2500 Colorado Avenue. Santa Monica, California/P/24, OB. State University, 56, Occupation Teacher. Stoyan, E1 Ioter/Dataproc Ingr, Oil and Gas Conservation Board, 603 6th Avenue. SW, Calgary, Alberta, Ken/A, P in. Petroleum Engineering/21, Mech Engineering. Special Petroleum Section, 58, Petro. Liam Ingr. Tolpin, Gerald/Proctor's Analyst, Ray. Thiel, Maynard, Mass/UP/29, Boston. University, 5, I, PGRMR/MBR, ORSA. Warlick, Charles H/MGR, Mathla Plus. Development, GECO, Comps Operation. Flight Propulsion Lab, GECO, Building. 305, Cincinnati 15, Ohio/AMP/30. University of Maryland, 52, MGR of a group. Engaged in residential in numerical and applied. Mathla analysis/co-author with D1. Young, on the use of Richardson's method for the numerical solution of Laplace's equation, BRLMEM report. 707, 52. Warren, Leland C/Methods Analyst, BAL. Timory and, Ohio Railroad, Methods Re. Search and Proctors Department, BN0RR, Sen. Trowel Building, Baltimore and Charles STS, BAL. Timory, MD/ABP/26, Wharton School of the University of Pa, 58, Systems and Proctors Analyst and PRGMR for Data. Matic 1000/MBR, Systems and Proctor. Association of America, American Statistical Association. White, Patrick J/Chief, Data PRCG Branch. Cons Office, Army Ordnance Corps. Frankfurt Arsenal, Tacony and Bridge STS. Philadelphia 37, PA/Ablum/30-5 \dig. Compare SYSADM/developed first payroll. And Levicht Contrippeln for Army. Ordnance Corps. Right, John H/MGR of Customer Serve. And EDUC, Daystrom, Inc., Control SYS. Thames DIV, 1. EDUC/25, MIT, 59, Serve MGR. Wrigley, Charles F/Prof of Psychology. Department of Psych, Mitch State University, East. Lansing, Mitch/17, University of London. PhD, 51, University Prof/USC Oven. Elect compare in principal axis factor. Analysis JEDUC Physical Col 55. Young, William E. L/Chief, Data Proc. CTR, Ohio Department of Finance, Columbus. Ohio/BP/16, Capital University, Ohio. State University, Case INST, Industrial College of Armed Forces, 42, Punched Card/PAR. Participating author of Punched Card. Newell, Gill Association, author of magazine. Articles and lecturer on ADP. Zager, Herbert I/Engineering Scientist Consult. And, RCA, 75, Varick Street, New York, NY. /Ulm/16, New York University, 46. Physicist/Publications in Reliability, SYS. Analyst, NLLCLR Physics, Operations Res. Consultant at Convair, San Diego, California and GE Co., Santa Barbara, California. Only DIN offers a combination of core memory and core logic that drastically reduces the semiconductor count in the circuitry required for control, address, drive, decoding, format conversion, and fullness control. Every one of DIN's 264 standard sequential access buffer designs employs this exclusive feature. You will find, therefore, that these buffers are remarkably compact, significantly lower in cost, and far more reliable than ordinary equipment designed for equivalent performance. R. U. TLIA is Man. SR. Computer Scientist. H. Nywell's Applied Research Group. Offers a challenging career opportunity to an individual qualified to conduct applied research in advanced digital computer, organizations and compute. Meth, DS for real-time application. Work involves developing original concepts to take advantage of new and future digital components. Extensive experience in logic design, computer organizati, N, digital systems. C, computer PR, gram analysis, number systems. All qualified applicants will receive C, Considerati, and for implement without regard to race, creed, color or national origin. Send resume to Mr. Clyde W. Hansen, Technical Direct. Tour, Honeywell Air, 2600 Ridgeway. R. Ad. Miniapp, Lis 40, Mins, Ta. Honeywell. TJ. D and buffers can do more, too. The unique flexibility of magnetic logic, as applied by the most experienced digital magnetic engineering staff in the field, can route more data, in more complex formats and programs, per dollar, per wow, and per cubic inch. Write for details. Your name will automatically be added to the list that receives our newest textbook, a handbook on the theory and application of sequential access buffers, off the press next month. At ILER_. 8 to 7700. ECFIC Digital/Analog Systems and Comp, NANS TWX Dorch 1057. Computers Mole Automation for July, 1961-27. 28. BOOISN. Other. Publicati, N.S. Moses M. Berlin. Alston, Mass. We publish here seed lions and brief reviews of books and other publications which have a significant relation to computers, data processing, and automation, and which have come to our attention. We shall be glad to report other information in future lists if a review copy is sent to lists. The plan of each entry is author or editor / title / publisher or issuer / date, publication process, number of pages, price or its equivalent / comments. If you write to a publisher or issuer, we would appreciate your mentioning C. Computers and Automation. Ackoff, Russell L., editor. I progress in Operations Research, Volume, II Jalm Wiley and Sons Incorporated, 440 Park Avenue, South, New York 16, NY. I 1961, printed, 505 pp. $11.50. This book contains a great deal of information on technical progress in the field of operations research, with emphasis on applications, unsolved problems and the state of the art. The first of 11 chapters, by the editor, discusses the meaning, scope, and methods of operations research. Subsequent chapters include dynamic programming, sequencing theory, the theory and application of simulation in operations research and military gaming. Philip M. Morse, of M1 TS Computation Center, discusses dynamics of operational TEMS, Markov and queuing processes. Author and subject indices: Rees, Paul K. and Fred W. Sparks ICOL. Leg Algebra, 4th edition. I. McGraw. Hill Book Co., Inc., 330 West 42 St. New York 36, NY. I 1961, printed. 428 pp. $6.50. This edition includes the information presented in the 3rd edition with revisions of certain material to satisfy the latest technological needs. In addition, new articles have been added on broken line functions, solutions of problems by means of simultaneous equations, effective rate and determination of the periodic payment, term, and rate. The book includes 22 chapters, beginning with the 4 fundamental operations and proceeding to exponents and graphs, ratio, proportion, and variation, higher degree equations, determinants, etc. An appendix includes answers to problems given throughout the text, a glossary, and mathematical tables. Index. Langer, Rudolf E., editor, and 19 authors. Partial differential equations and continuum mechanics. University of WIS. Consine Press, 430 Sterling Court, Matey. Sun 6, Wise. 1961, photo offset, 397 pp. $5. The 19 lectures which were delivered at the International Conference of the Mathematics Research Center, University City of Wisconsin, June, 1960, are here published. Among the titles and contributors, aspects of differential equations in mathematical physics, Klaus Miller, the angular distribution of eigenvalues of non-self-adjoint elliptic boundary value. Problems of higher order, Shmuel A.G. Mon, finite deformation of plates into shells, B.R. Seth, atypical partial differential equations, Hans Louis, etc. In addition, 42 abstracts of contributed papers are included. Index. Leeds, Herbert D., Ami Gerald M. Vane. Berg I. Computer Programming Funda. Mentals I. McGraw-Hill Book Co., Inc. 330 West 42 St., New York 36, NYI. 1961, printed, 368 pp, $8.50. For those with little technical background, this book is an excellent introduction to computer programming in general, and IBM 7090 programming in particular. Following a first chapter on what is a computer, the authors discuss the entire programming process from flow diagram to machine production runs. Among the 11 chapters are indexing, routines, introduction to input-output, and arithmetic. Lists of 7090 instructions and SOS, share operating system, pseudo operations, and an index, are included. Beckenbach, Edwin F., editor, and 16.0. Thor's I. Modern Mathematics for the Engineer, 2nd Series I. McGraw-Hill. Book Co., Inc., 330 West 42 St., New York 36, NY. I. 1961, printed, 456 pp. $9.50. The applications of advanced mathematics to current technological needs are discussed in 16 papers, given as a series of lectures 1958-59 at the University City of California. The applications include mathematical techniques used in biology, economics, sociology, and physics. The first part of the hook, Mathematical Methods, consists of 5 papers including From Delta Functions to Distributions, Integral Transforms, and Asymptotic Formulas and Series. Part 2, Statistical and Scheduling Studies, includes chance processes and fluctuations, in formation theory, formulating and solving linear programs, and the mathematical theory of inventory (PROC). Essays. Part 3, Physical Phenomena, includes Applications of the theory of partial differential equations to prob. Lems of fluid mechanics. Name and subject indices. Korn, Graninoe, and Teresa M. Korn. Mathematical Handbook for Scientists and Engineers. McGraw-Hill Book Co., Inc. 330 West 42 St., New York 36, NY. 1961, printed, 943 pp., $20. This handbook, encyclopedic in scope, presents reviews of important theory, formulas and definitions in a manner which allows for quick study and use. In 21 chapters, the authors include real and complex numbers, plane and solid analytic geometry, functions and limits, vector analysis, complex variable theory, ordinary and partial differential equations, matrices, differential geometry, probability theory, statistics, numerical analysis, and special functions. Example: Bernoulli polynomials and numbers. 6 appendices include information about trigonometry, permutations, and combinations, tables of Fourier expansions of indefinite and definite integrals, and the standard mathematical tables, example log, RITHMS, trigonometric functions, Bessel functions. Glossary of symbols and index. Computers and Automation for July 19, IL. YJ. Ha. The. Today. We see a. Day I1. Any. Has E. Ital L. Impo L. W. Inven. Night. Ordery. Have. 10%. Ducty. The. 1039 I. Koi. N. N. Shed. 1951. L7. 1, 6. 8. 10. 13. 15. 6. 6. 22. 22. 24. 28. 29. 30. E24. E12. E28. E12. E24. 9. 1. IL. New patents. Raymond R. Skolnick. Reg. Patent Agent. Ford Inst. Co., Div of Sperry Rand. Corp., Long Island City 1, New York. The following is a compilation of patents pertaining to computer and associated equipment fro the Official Gazette of the U.S. Pat. and Office, dates of issue as indicate. Each entry consists of patent number / inventor, s / assignee / invention. Printed copies of patents may be obtained from the U.S. Commissioner of Patents, Washington 25, D.C., at a cost of 25 cents each. January 24, 1961, counted 2,969,526. Igenang L. Clapper, Vestal. NY. I1.B.M. Corp., New York, NY. A method and apparatus for handling and storing binary data. 2,969,528. Itung Chang Chen, Haver. Town, Pa. I Burroughs Corp., Detroit. Equal. IA read-write circuit for Mag. Netic recording. January 31, 1961. 2,969,730 I Lyle W. Bram, Endicott. NY. IINM. Corp., New York, NYI. A data translation and printing Ma. Chine. 2,969,912 I Andrew C. Reynolds, Jr., WA. Tilbury, Con. I1.BR. Corp., New York, NY. I an error detecting and correcting circuit. 2,969,913 I Alvin H. Aaron, Torrance. And Rahert R. Johnson, Altadena, California. I Hughes Aircraft Co., Culver City, California. I circuits for selectively shifting, extracting, and inserting DG. TAL information. 2,970,293 I John P. Eckert, Jr., Philadelphia, PA. I Sperry Rand Corp., a corp of Dell I. A binary counter. 2,970,294 I Sadia Escuterman, Dorchester, Mass. I Raytheon Co., a corp. of Dell. I a magnetic control circuit for shift registers. 2,970,296 I Paul V. Horton, Poughkeepsie, NY. II.BR. Corp., New York, NY. IA printed circuit Ferrite core MEM. Ori assembly. 2,970,297 I John A. Kaufman, Hyde Park, NY. II.BR. Corp., New York, NY. IA magnetic branching circuit. For handling binary information. 2,970,298 I Frank J. Prines, Penn Hills Township, Allegheny County, PAI. Westinghouse Electric Corp., East Pitts Burg, PA. IABIST Able Circuit. 2,970,299 I Herman Epstein, Westchester. And Oscar B. Stram, Pauli, PA. I Burr. Ruffs Corp., Detroit, Mich. I Electro. Graphic recording with magnetic material. 2,970,300 I Victor R. Witt, Poughkeepsie. Peter 1. Prentke, \Vappingers Falls. NY, and Erwin K. Dudek, Pal. Keepsy, NY. IIBM. Corp., New York, NY. IASQ Elimination System. 970,306 I Henry E. Zeman, Lexington, Massachusetts, and Juhus I Wolf, Levittown, PA. I Research Corp., New York, NY. A digital to analog decoder circuit. 2,970,308 I George A. Stringfellow and Erwin J. M. Cure, San Diego, California. I. General Dynamics Corp., San Diego, California. IA Para CL Digital to AC. ANA. Log Convert CR. Header. Instrument Company Incorporated, Plainview, New York. Computers Alt Automation for July, 1961-29. Dash. I. Comma. CRT display. We are far out in front in the design and construction of airborne systems which utilize display consoles. Scientists and engineers who are interested in digital display, video, and deflection CIR. Quit design for these consoles will find profit in writing to R. Mr. S. L. Hirsch. RN. Litton Systems Incorporated. Tactical Systems Laboratory. Canoga Park, California. J. 2,970,309 I William B. Towles, Timo. Niam, MD. IUSA as represented by the seconds of the Navy I an analog to digital dot converter. February 7, 1961. 2,970,759 I Walter C. Lanning, Plainview. NY. I Sperry Rand Corp., a corp of Dell. I an absolute value reversible. Counter. 2,970,761 I Raymond Berenger, Paris, Fr. I North American Philips Co., Inc. New York, NY. I a digit indicator. Employing a shift register. 2,970,763 I Herbert Freeman, Great Neck. NY. I Sperry Rand Corp., a corp of Dell. I a predetermined pulse selector. 2,970,764 I William J. Deerhake, Dumont. Byron L. Havens, Closter, and Kenneth E. Schreiner, Harrington Park, and J.I. IBM, Corp., New York, NY. IA. Checking circuit for determining whether a multi-decimal position word expressed in binary decimal notation and the indicator of said work are in accord. 2,970,765 I Raymond Bird, Letchworth. Eng. I International Computers and Tabulators Lim, a British co. IA. Data Translating Apparatus. 2,970,766 I Herman Epstein, Wessel. Chester, Pa. I Burroughs Corp., Detroit. Mitch. I a binary multiplier employing a delay medium. 2,971,056 I Alan J. Deerfield, Franklin. Mass. I Minneapolis Honeywell Rego. Later Co., Minneapolis, Min. I an in. Formation handling apparatus. February 14, 1961. 2,971,696 I Robert A. Hennell, Hyde Park. NY. I IBM. Corp., New York, NY. I a binary adder circuit. 2,972,060 I Robert D. Torrey, Philadelphia, PA. I Sperry Rand Corp., a corp of Dell I. A logic circuit for producing complement output signals. 2,972,062 I Orner P. Clark, New Vernon. NJ. I Bell Telephone Lab, Inc., New York, NY. I a transistor binary. Counter. 2,972,063 I Arthur W. Carlson, Harrison. Main IUSA as represented by the seconds of the Air Force I an impulse responsive circuit for binary counting. 2,972,082 I Hartmut P. Coleman, Flush. Ing, and Barnett Rosenberg, New York. NY I Research Corp., New York. NY. I a data storage method and AP. Paratus. 2,972,128 I John P. Eckert, Jr., Gladwine. John C. Sims, Jr., Springhouse, and Herbert F. Welsh, Philadelphia, PA. I Sperry Rand Corp., New York, NY. IA Phase. Modulated Pulse Recording System. 2,972,130 I Robert C. Minnick, Cam. Bridge, Massachusetts I Bell Telephone Lab. Inc., New York, NY. IA Magnetic Core Storage circuit. 2,972,131 I. Gerhard Dirks, Frankfurt, GER. I apparatus for sorting SIG. Nals recorded on a magnetizable signal. Carrier. 2,972,136 I. Luther P. Giesler, Rockville. MD. IA Data Handling SYS. TEM and Magnetic Switching Network. Therefore. February 21, 1961. 2,972,718 I. Norman N. Alperin, Cinna. Minson Township, Burlington County. And Warren A. Mull, Morristown. NJ. IUSA as represented by the Seconds of the Navy IA synchronized. Sampled data digital servo. 2,972,733 I. J. Fred Busey, Jr., Dallas, Tex. I. Texas Instruments Incorporated, Dallas, Tex. IA Method and Apparatus for Analyzing Data. 2,972,735 I. Harrison W. Fuller, Boston. And Robert C. Kellner, Concord, Mass. I. Lab for Electronics Incorporated, Boston, Mass. IA Data Processing System. Advertising Index. Following is the index of advertisements. Each item contains name and address of the advertiser / page number. Where the advertisement appears / name of agency if any. Aeronotronic DIV. Ford Motor Co., Newport Beach, California. /page 32. I. Honig Cooper and Harrington. Automatic Electric, Northlake, Ill. /page 2 / Kudner. Agency Incorporated. Burroughs Corp., Detroit 32, Mich. /page 7 / Campbell. Ewald Co. Dis/and Controls Incorporated, 944 Dorchester Avenue, Boston 25. Mass. /page 27 / Keys, Martin & Co. Electric Boat, a DIV of General Dynamics, Groton, Con. /page 17 / Darcy Advertising Co. Honeywell Aero, Minneapolis Honeywell Regulator Co. 2600 Ridgeway Road, Minneapolis 40, Min. /page 27 / Batten, Barton, Durstine and Osborne Incorporated. 30. Hughes Aircraft Co., Culver City, California. /page 28 / Foot, Cone and Belding. Litton Systems Incorporated, Tactical Systems Laboratory, Canoga Park, California. /page 30 / Compton Advertising Incorporated. The Miter Corp., P.O. Box 208, 5 Mu, Bedford, Mass. /page 31 / Deutsch and Shea Incorporated. The National Cash Register Co., Dayton 9, Ohio /pages 5, 23 / McCann Erickson, Inc. Philco Corp., Government and Industrial Group, Computer. DIV, 3900 Welsh Road, Willow Grove, Pennsylvania. /page 3 / Maxwell Associates Incorporated. Potter Instrument Co., Inc., Plainview, NY. /page 29 / Gamut Incorporated. Reeves Soundcraft Corp., Great Pasture Road, Danbury. Con. /page 26 / The Wexton Co., Inc. Remington Rand Univac, Univac Park, St. Paul, Min. /page 25 / Mullen and Associates Incorporated. Computers and Automation for July, 1961. 1961. MITRE is a 11011 profit. System L1 Giliridalg. Orowal 1 is Ashol Elgijt. Il the design. DCL allotment and CL al Yashol 1 of CL 11 Lal 1 D Ald. CL Tral. Systems. Engineers and scientists. Satin is an example of MITRE's pioneering efforts in large control systems. Excellent. Opportunities are currently available in this program for well-trained engineers, mathematicians, and physicists with active, inquiring minds. If you have an interest in computers, communications, control systems, or aircraft and like, to put new ideas to work, there may be a place for you in MITRE's expanding air traffic control activities. Openings are also available at MITRE's facility in Montgomery, Alabama. Inquiries may be directed in confidence to Vice President, Technical Operations. A brochure more fully describing M11RE and its activities is available upon request. ::::::::::::::::::::::::::::::::::::::::::::::::::::::::::::::::::::::::n MITRE plus LIIIX I40 IT plus ELK GL$LL Post Office Box 208 5 Mu Bedphone L 1 Has Trilil Sets. All qualified AP1 ICL 1 TS will receive COL1 consideration for employee LILD with all regard to race, creed, color or national origin. Computers and Automation for July, 1961-31. BIAX memories are the answer. Aeronautics BIAX instruction memories will increase the speed of your computer, data handler, or control system. These remarkable memories operate 8 at high speed, with non-destructive read, low power, and high reliability. BIAX memories offer access time of 0.4 USEC and cycle time of 1.0 USEC without need for regeneration. These advanced memory systems will give you the necessary speed and reliability for all your program. Storage specifications: up to 1024 words, up to 36 bits per word. Read cycle time 1.0 USEC. Access time 0.4 USEC. Loading from paper tape or your equipment at rates up to 200 kc. Power less than 50 watts. Temperature 0 degrees C to 50 degrees Celsius. BIAX memories are available in several standard sizes or can be built to your specifications on a fixed price basis. Their low power requirements plus high reliability over a broad range of environmental conditions assure dependable performance. For further information regarding BIAX memories capability applicable to your requirements, you are invited to write or call Manager of Marketing, Computer Products Operations, Department 27, Aeronautics Division, Newport Beach, California. T. Co. AP